Hello there, and welcome to the Cosmographer. 124 light-years from here, in the atmosphere of a single distant planet, our telescopes may have caught the faint scent of a gas that, on Earth, only living things are known to make. That is one of 10 real discoveries on tonight's list, each of which leans, in its own strange way, toward the possibility that we are not alone. Among them is a star flooded with elements that should not exist, another that appears to have been quietly going out across 100 years of photographs and 72 seconds of radio noise, recorded in 1977, that has never returned and never been explained. Among them is a visitor from another star, studied harder than any before it, and at the very end, the one object we have never been able to account for at all. Not one of these is proof. Not one has been closed. Get comfortable and settle in. If 3 hours of the universe's open questions is your idea of a good night, a quiet like and subscribe genuinely helps this channel find more people like you. Because by the end of this countdown, you will understand why we may be living in the exact window of history when these questions finally begin to get their answers. Let's begin at number 10. Number 10. Titan's impossible chemistry. There is one question older than every telescope, older than every map, older than the first person who ever gave a name to a star. It is the question of whether anything else is out there. Tonight, we are going to walk through 10 real answers to that question, or rather, 10 real attempts at it. Each one is a genuine discovery, made by named people on known dates with instruments we can point to. And each one, in its own quiet way, leans toward the possibility that we are not the only thing that ever happened in the universe. None of these 10 is proof. That has to be said clearly at the start, because it is the most honest thing in the whole list. Not one of these discoveries has closed the question with a confident yes, but not one of them has been closed with a confident no either. They are the results that sit in the middle, the ones that will not resolve, the ones that keep good scientists arguing in careful language decades after the fact. That is exactly why they belong here. The strangeness of this list is not manufactured. It is simply what happens when you look closely at what we have actually found. We are going to count down from number 10 to number 1, and the ranking follows a single thread. Near the top of the list are the gentlest hints, the chemistry, and the places that could, in principle, cradle life. As we descend, the discoveries turn from life to intelligence, from worlds that might be habitable to things that made serious astronomers ask, out loud and in print, whether something had been built. And at the very bottom, at number 1, sits the single object whose behavior we still cannot explain, an object that passed through our solar system once, sped up as it left, and never told us why. The register tonight stays calm the whole way down. These facts are unsettling enough on their own. Delivered slowly, with the names and the numbers kept intact, they hold their weight without a single raised voice. Where a discovery has a good, ordinary explanation, we will give that explanation plainly. Where the ordinary explanation is still contested, we will say so. You are trusted to sit with an open question and to find it more interesting for staying open. One more thing, before we start the descent. You may notice as we go that the discoveries fall into a shape. Near the top of the list, at numbers 10 and 9 and 8 and 7, we are looking at chemistry and at worlds, at the raw ingredients and the possible traces of life, mostly microbial, mostly ancient or far away. Then, around the middle of the list, something shifts. The discoveries stop being about whether something could live somewhere, and start being about whether something was built, whether some other mind, somewhere, left a mark we could detect. And at the very bottom, at the last few numbers, we arrive at the single events and single objects that have resisted every ordinary explanation offered so far, the ones that refuse to close. That shape is deliberate, and it is worth holding in your mind as we go, because it is the shape of the question itself, widening from life to intelligence to the genuinely unexplained. So let us begin, and we begin not with a signal, and not with a machine, but with a moon, where the rain is not water. Saturn's largest moon is called Titan, and it is the only other body in our solar system with standing liquid on its surface and a thick atmosphere overhead. In that one sentence, it sounds almost like home, but nothing else about it is. The liquid on Titan is not water. Its surface sits near -179 degrees Celsius, cold enough that water there is not a liquid at all. On Titan, water is rock. It is bedrock, hard as granite, part of the ground itself. What flows across that ground, what pools into lakes and carves rivers and falls from the sky as rain, is methane and ethane, the gases we burn for heat on Earth, held as cold liquid under an orange haze. Titan has seas. They have names. Kraken Mare, Ligeia Mare, Punga Mare, mapped by the Cassini spacecraft as it flew past again and again over more than a decade. These seas are filled with liquid natural gas beneath a thick nitrogen sky the color of dark honey. If you could stand on the shore of Kraken Mare, you would see waves and shorelines and weather, and none of it would be made of anything you could drink. It is a world that has borrowed the shape of Earth and filled it with the wrong material. This is why Titan matters so much to the people who study the question of life. It forces them to confront a bias they have named, and the name is telling. They call it water chauvinism. It is the quiet assumption, natural because every single living thing we have ever known depends on it, that life must be built around liquid water. We assume water because we are made of it. But the assumption has never been proven to be a law of the universe. It might only be a description of home. And Titan is the place that makes that distinction impossible to ignore. To see why, you have to look at what a cell actually is. Every living thing on Earth, from the largest animal to the smallest microbe, is built out of cells, and every cell is wrapped in a membrane. That membrane is not a small detail. It is the wall that makes life possible at all. It separates the ordered, careful chemistry of the inside from the chaos of the outside. It decides what comes in and what stays out. Without a membrane, there is no inside, and without an inside, there is no cell. On Earth, that wall is built from molecules called lipids, and lipids work beautifully in water. They arrange themselves automatically into flexible sheets, oily on one side, water-friendly on the other, and they hold together with a kind of quiet reliability that life has depended on for billions of years. But drop an Earth membrane into liquid methane, into the seas of Titan, and it fails at once. The cold locks it rigid. The chemistry that made it flexible in water does not work in a hydrocarbon sea. It would freeze hard and crack apart. Water-based life, the only kind we have ever met, simply cannot function in Titan's oceans. So the question Titan poses is precise, and it is strange, and it is one of the most interesting questions in all of science. Could a membrane be built out of something else, something that stays soft and flexible in liquid methane at nearly -180 degrees? If the answer is no, then Titan's seas are just cold solvent, chemically dead, beautiful and empty. But if the answer is yes, then the requirement everyone assumed was universal was only ever a local habit. And the universe would have just doubled the number of places life could take hold. For a long time, this stayed a thought experiment, the kind of thing you could argue over but never test. And then the chemistry of Titan itself began to answer back. In the year 2017, a group of researchers combined archived data from the Cassini spacecraft with fresh observations from a remarkable instrument in the high desert of northern Chile, the Atacama Large Millimeter Array, a field of dishes that listens to the faint radio glow of molecules in distant atmospheres. Together, these instruments confirm the presence of a specific molecule in Titan's air. The molecule is called vinyl cyanide. Chemists also write it as acrylonitrile, and it was not present in trace amounts. It was there in enormous quantities, forming high in the haze and, by the estimates of the models, raining down toward the seas below by the ton. On its own, a molecule in an atmosphere is just a molecule. What made vinyl cyanide matter had been worked out slightly earlier by a team at Cornell University. They had asked a very particular question. If you wanted to build a cell membrane in liquid methane at Titan's temperature out of the ingredients Titan actually has, what molecule would you need? They ran the chemistry in simulation, testing which compounds could link themselves together into a stable, flexible, hollow sphere in that frozen environment, the cold world equivalent of a living cell's wall. And out of the candidates, vinyl cyanide came out strongest. It could, in the models, assemble itself into exactly the kind of microscopic sphere a membrane needs to be. The researchers gave the theoretical structure a name. They called it an azotosome, from the French word for nitrogen, azote. Now hold the two halves of this together, because that is where the strangeness lives. On one side, a model said that if a cold world membrane could exist, vinyl cyanide is the molecule that would build it. On the other side, an instrument looked at Titan and found vinyl cyanide there in abundance, forming constantly, falling into the seas. The ingredient the theory called for turned out to be genuinely present, in genuinely large amounts, on a genuinely real world. That is the entire discovery, and it is enough to make you sit up quietly in the dark. Titan has the chemistry that a membrane without water would need. An azotosome is not life. It is important to be exact about that. It is not a cell, and it is not evidence of a cell. It is the possibility of a container for life, a wall that could hold an inside apart from an outside, in a place where the walls we know cannot exist. It is the architecture, standing empty, with no proof that anything ever moved in. And later work has been careful to question how readily these spheres would actually form and hold together in the real conditions of a Titan sea. The point was never that they certainly exist. The point is that the required material is really there, really falling, really waiting. The scale of the place makes it stranger still. Titan's seas hold more liquid hydrocarbon than all of Earth's proven reserves of oil and gas combined, an entire world's worth of the wrong kind of ocean, sitting quietly under that orange sky, cold and full and unexamined. We have flown past it. We have mapped its coastlines from orbit. We have even once dropped a probe through its atmosphere and landed on its surface, a European lander called Huygens, that sent back pictures of a shoreline made of water ice and channels cut by methane rain. But we have never sampled the chemistry of those seas directly. We have never asked them the only question that matters. Not yet. There is something worth sitting with in that gap, between having the ingredients and having the answer. Titan has been running its slow chemistry for billions of years, in the cold and the dark, with the raw material for a membrane falling steadily into its seas the entire time. Whether anything ever came of it, whether that chemistry ever crossed the line into something that could grow and copy itself and be called alive, is a question the moon has kept to itself. We have mapped its coastlines and touched its ground and measured its air, and still we do not know the one thing we most want to know. That is often how it goes in this search. The evidence accumulates, the possibility sharpens, and the final answer stays just out of reach, waiting for a better instrument or a closer look. That is about to change. A mission called Dragonfly is on its way to Titan, a nuclear-powered rotorcraft, a machine that will fly between locations on the surface and sample the chemistry it finds. It is the first real chance to test whether Titan's chemistry ever took the next step, whether the ingredients that could build a membrane ever did, whether anything on that cold moon ever crossed the line from chemistry into something that could be called alive. We do not know the answer. We will not know it for years. But the question is no longer only a question. It is now a place we are going to visit, with an instrument built to listen for exactly this. It is worth pausing on how much we already know about this world, because Titan is not a rumor. It is a place we have visited. The Cassini spacecraft spent years in the Saturn system, and again it flew close to Titan, using radar to see through the permanent orange haze that hides the surface from ordinary cameras. Those radar passes mapped the seas, traced the coastlines, measured the depths of the larger basins, and found river networks branching across the land exactly the way rivers branch on Earth, cut not by water, but by liquid methane over long ages. Titan is the only world besides Earth where we have mapped standing bodies of surface liquid, and the maps are detailed enough to give the seas their names and their shapes. We have even touched it. In early 2005, a European probe called Huygens, carried to Saturn aboard Cassini, detached and parachuted down through Titan's thick atmosphere, sending back data the whole way and surviving its landing on the surface. The pictures it returned showed a landscape of rounded pebbles made of water ice, scattered across a plain that appeared to have been shaped by flowing liquid, a dry channel bed under a hazy sky. It remains the most distant landing humanity has ever achieved, a machine resting on the shore of a methane sea, more than 1 billion kilometers from home. So when we talk about the chemistry of Titan, we are not speculating about an abstraction. We are talking about a real, mapped, visited world, whose seas we have charted and whose ground we have stood a probe upon. The atmosphere itself is part of the strangeness and part of the promise. Titan is wrapped in a thick nitrogen atmosphere, denser at the surface than Earth's own, the only moon in the solar system with a substantial atmosphere at all. High in that atmosphere, sunlight and energetic particles break apart the nitrogen and the methane and drive a rich, complex chemistry, building larger and larger organic molecules that drift down as a fine orange smog, the haze that gives Titan its color. That constant rain of organic material, sifting down onto the surface over billions of years, has made Titan a kind of natural laboratory for the chemistry that comes before life, the same broad family of reactions that many scientists think were at work on the early Earth. Titan is cold, far colder than any cradle of life we know, but it is running the experiment. It has the raw material, the energy, the liquid, and the time. What it may not have is warmth, and whether that matters is one of the deepest open questions in the search for life at all. And here is what Titan leaves us with before we move on. If a wall for life can be built without water, then the one assumption that made Earth feel unique, the belief that life needs what we need, was never a rule at all. It was only ever a description of the one example we had. Titan does not prove that life exists elsewhere. It proves something subtler and, in its way, more unsettling. It proves that the universe is not obligated to build life the way it built us. The seas do not have to be water. The rain does not have to be rain. And if the container can be built without the thing we thought was essential, then the next world on our list asks an even stranger question. Not whether a sea could hold life, but whether the sea itself could be staring back. Number 9. The Eyeball Ocean. 48 light-years from here, in the faint southern constellation of Cetus, the sea monster, there is a small, dim, red star. It is a red dwarf, cooler and smaller than our Sun, the most common kind of star in the whole galaxy. And circling it, once every 25 days or so, is a planet named LHS 1140b. For years, this planet was one of the most frustrating puzzles in the search for other worlds, because it sat exactly on a line between two completely different fates, and no one could tell which side of that line it was on. Here is the puzzle. LHS 1140b orbits inside its star's habitable zone. That phrase gets used a great deal, and it deserves to be said carefully. The habitable zone is the band of distance around a star where a world can, in principle, hold liquid water on its surface, neither so close that the water boils away, nor so far that it freezes solid forever. It is not a promise of life. It is only a promise of possibility, the right amount of warmth. And this planet sits squarely inside it, receiving from its small red star roughly the gentle warmth that would keep water liquid. But warmth is not enough to know what a world is. The trouble was its size and its weight. When astronomers measured how much LHS 1140b bends its star's light and tugs on its star's motion, the numbers left it stranded between two identities. On one reading, it could be a dense, rocky super-Earth, a solid world larger than our own but built of stone and metal, with a thin atmosphere clinging to a real surface. On the other reading, it could be a miniature version of Neptune, a small rocky core buried under a deep, crushing envelope of hydrogen and helium gas, thousands of kilometers thick, with no surface worth the name and pressures that would flatten anything that tried to live there. The difference between those two worlds is the difference between hope and a dead end. A mini Neptune, smothered in hydrogen, is not a place where life as we understand it could ever begin. But a rocky planet with the right kind of air, sitting in the habitable zone of a star just 48 light-years away, is one of the most promising addresses anyone has ever found. And everything, the entire question, came down to one thing that had never been possible before. It came down to reading the planet's atmosphere from across all that distance. That is a genuinely difficult thing to do. A planet is a speck next to the blazing face of its star. To read its air, astronomers wait for the planet to pass in front of the star from our point of view, and in that moment, a thin sliver of starlight filters through the planet's atmosphere on its way to us. The gases in that atmosphere each absorb their own particular colors of light, leaving faint, dark gaps in the spectrum, a kind of chemical fingerprint written in shadow. Reading those gaps means separating the whisper of a planet's air from the roar of an entire star. For most of history, it was simply impossible. Then we built a telescope that could do it. In the year 2024, the James Webb Space Telescope turned its golden mirror toward LHS 1140b and read the light. And the answer came back on the hopeful side of the line. The data strongly disfavored the hydrogen-rich mini-Neptune scenario. This was not a small, gassy failure of a world crushed under an envelope of hydrogen. Instead, the observations pointed to a dense, rocky planet wrapped in a secondary atmosphere, an atmosphere most consistent with being dominated by nitrogen. Nitrogen. The same gas that makes up most of the air moving in and out of your lungs at this very moment. Nearly 4/5 of Earth's atmosphere is nitrogen, and here was a hint of the same gas, wrapped around a rocky world in the habitable zone of a nearby star. In the careful, understated language that this field insists on, that is called extremely interesting. In plainer words, it is one of the best candidates for a habitable ocean world that anyone has ever identified beyond our own solar system. To understand what such a world might look like, you have to think about how it turns, or rather, how it does not. Because LHS 1140b orbits so close to its dim red star to stay warm, the gravity between them is powerful, and that gravity has almost certainly locked the planet in place. Astronomers call it tidal locking. It means the planet keeps one face turned toward its star at all times, the way our own moon keeps one face turned always toward Earth. One hemisphere lives in permanent, unmoving daylight. The other hemisphere is held in an endless, frozen night that no sunrise ever reaches. Tidal locking is worth understanding, because it is the fate of a great many of the most promising planets we find, and it shapes everything about them. When a planet orbits close to its star, the star's gravity pulls harder on the near side of the planet than the far side, and over long ages this difference acts like a brake on the planet's spin, slowing its rotation until, eventually, the planet turns exactly once for each trip around the star. The result is that the same face is held toward the star forever. Our own moon does this with respect to the Earth, which is why we only ever see one side of it from the ground. For a planet in the habitable zone of a small red dwarf, tidal locking is almost inevitable, because such planets must orbit close in to stay warm, and closeness is exactly what drives the locking. So the eyeball arrangement, one hemisphere in eternal day and one in eternal night, is not a rare curiosity. It may be the normal condition of the most common potentially habitable worlds in the galaxy, which makes understanding whether life could survive on such a world one of the central questions of the whole search. On a bare rock, that arrangement would be lethal to any hope of water. The day side would bake under its unblinking sun, and the night side would freeze into a dead, airless waste, with everything that could flow having long since fled to the cold side and locked itself into ice. But an atmosphere changes everything. A thick blanket of nitrogen can carry heat around the planet, from the scorched day to the frozen night, softening both extremes, and that is where the models of LHS 1140b become genuinely beautiful. With that nitrogen blanket in place, the climate simulations suggest something that reads like a scene from a novel. They suggest an eyeball world. Picture it. Across the entire night side, and reaching around toward the edges of the day, the planet is sheathed in a shell of thick glacial ice, white and hard and old. But directly beneath the star, at the point on the day side where the sun stands permanently overhead, the ice melts completely. There, and only there, a wide ocean of liquid water opens up, warm and standing and stable, staring straight up at the star that keeps it from freezing. Seen from space, the planet would look like a single enormous eye. A round blue ocean, the iris, set in a wide white expanse of ice, the sclera, gazing without blinking at its own sun. That is why they call it an eyeball planet. The ocean at the center of that eye could be thousands of kilometers across. And because it sits beneath a star that neither rises nor sets, it could hold steady, temperate conditions for an extraordinarily long time, no seasons, no day and night, just a permanent mild noon over an open sea. Around the edge of that ocean, where the warm water meets the encroaching ice, there would be a ring of twilight, a band of shoreline wrapped all the way around the planet where the light comes in low and level forever. That ring, the terminator, the boundary between the melting day and the frozen night, would offer some of the most stable and varied real estate on the whole world, a temperate margin between fire and ice. Imagine standing on that terminator, the twilight ring where the ocean meets the ice. The star hangs low and unmoving on the horizon, neither rising nor setting, a dim red disk that never climbs and never falls, casting a permanent, level light, the color of a long sunset. Behind you, toward the frozen hemisphere, the ground rises into an immense sheet of glacial ice stretching off into a night that never ends. In front of you, toward the star, the ice gives way to open water, a sea warmed by that low red sun, calm and steady and stretching to the horizon. There is no day here in the way we know it, and no night, only this endless margin between them, this one band of shore wrapped all the way around the world, where the temperature holds mild and the light holds constant. If there is anywhere on such a world that a living thing might find a home, it is here, on the ring of permanent evening between the fire and the ice. That is the picture the models paint, and it is worth holding in the mind, even as we remember that it is a picture drawn from measurements, not a place anyone has yet seen. It has to be said clearly what is known and what is imagined here. The eyeball is a model, not a photograph. What the telescope actually established is that LHS 1140b appears to be rocky, and that it appears to carry a nitrogen-rich atmosphere rather than a crushing hydrogen envelope. Those two findings are the real, measured discovery. The standing ocean staring out from the substellar point is the leading interpretation that follows from them, not a sea anyone has yet seen. No one has photographed that iris. No one has measured that shore. What we have is a rocky world, in the right place, with the right kind of air, and a climate model that turns those facts into an ocean. But that, in itself, is a change in what humanity is able to do. For all of history, an ocean on another world was something you could only imagine, a setting for stories. Now, for the first time, we are not imagining a nameless sea in fiction. We are pointing a real instrument at a specific rocky planet with a real designation, 48 light-years away, and finding the ingredients for a real ocean staring back. The distance is close enough, by the scale of these things, that future telescopes may one day be able to search that atmosphere for the fingerprints of biology directly, to ask not only whether there is a sea, but whether anything lives in it. It helps to understand how hard-won this planet was, because LHS 1140b was not found in a single night. It was discovered by watching its star dim, very slightly and very regularly, each time the planet crossed the face of the star from our point of view, a technique called the transit method. That dimming is tiny, a fraction of a percent, and it takes many careful passes to be sure it is real and not noise. Then, separately, astronomers measured the way the planet's gravity tugs its star back and forth, a subtle wobble that reveals the planet's mass. Only by combining the two, the size from the transits and the mass from the wobble, could they work out the planet's density, and it was that density that stranded it for so long between the two possible identities, rocky world or miniature Neptune. Years of patient measurement went into pinning down the numbers before the James Webb Space Telescope could finally read the air and break the tie. There is a shadow over red dwarf worlds like this one, and honesty requires naming it. Red dwarf stars, for all that they are small and cool and long-lived, are often violent in their youth and beyond. They can unleash powerful flares, sudden bursts of radiation far larger, relative to the star, than anything our own steady sun produces. A planet orbiting close to such a star, close enough to stay warm, sits directly in the path of those flares, and over billions of years, that radiation can strip away an atmosphere and sterilize a surface. This is the great open question hanging over every potentially habitable red dwarf planet, and there are many of them, because red dwarfs are the most common stars in the galaxy. Can a world hold on to its air, and any life that air might shelter, under the repeated fury of its small, angry sun? For LHS 1140b, the very fact that Webb detected a substantial nitrogen atmosphere is encouraging, because it suggests the planet has managed to keep its air, despite everything. But the question is not closed, and it applies to a huge fraction of the worlds we most want to hope for. What makes LHS 1140b especially valuable is its nearness and the geometry of its orbit. At 48 light-years, it is close by the standards of these searches, and because it transits its star, passing directly in front of it from our line of sight, we get repeated chances to read its atmosphere in the filtered starlight. The next generation of instruments, both the giant telescopes now being built on the ground and the space telescopes already flying, will return to this world again and again, building up the signal, searching that nitrogen air for the specific gases that on Earth are associated with life. If there is an ocean at the center of that frozen eye, and if anything stirs in it, this is one of the handful of worlds where we might, within a generation, actually find out. It is not a story we are telling ourselves. It is a target on a list of things to observe. And that is the quiet turn LHS 1140b leaves us on. A world that could hold an ocean is a remarkable thing to find. But an ocean is only a place. It is a container, like the membrane on Titan, a setting where life could happen, with no word yet on whether it did. A possible ocean is one kind of hint. A gas that only life is known to make is another kind entirely. And on the next world down our list, more than 100 light-years from that staring blue eye, we may have caught the faint chemical scent of exactly that. Number 8. The gas only life makes. 124 light-years from here, in the constellation Leo, the Lion, a planet named K218b, circles another small red dwarf star. It is a world unlike anything in our own solar system. It is a sub-Neptune, about 8.5 times the mass of Earth, larger than any rocky planet we know, but smaller than the ice giants that guard our own outer system. For a long time, worlds of this size were a mystery, because we have no example of one nearby to study. There is nothing between Earth and Neptune in our own family of planets, a strange gap in the sizes, and K218b sits right in the middle of it. And it sits inside its star's habitable zone, in the band where liquid water is possible. Some astronomers believe K218b may belong to a proposed new class of world, one that does not exist in our solar system at all. They call these worlds Hyxian planets, a name stitched together from hydrogen and ocean. The idea is striking. A Hyxian world would be a planet with a single deep, global ocean of liquid water, wrapped not in an Earth-like atmosphere of nitrogen and oxygen, but in a thick blanket of hydrogen gas. No continents, no islands. Just one warm sea covering the entire planet, with a hydrogen sky pressing down on it from horizon to horizon. If that picture is correct, then K218b is not a rocky Earth twin. It is an ocean under a hydrogen sky, and its entire atmosphere becomes a chemistry experiment that we can read from 124 light-years away. The idea of a Hyxian world deserves a little more attention, because it changed how astronomers think about where life might be found. For a long time, the search for habitable planets focused on finding another Earth, a rocky world of about the right size, at about the right distance from a sun-like star, with liquid water on an exposed surface. That is a narrow target, and such worlds are hard to study because a small rocky planet has a thin atmosphere that gives up very little information to our telescopes. The Hyxian concept widened the target dramatically. It proposed that a larger world, wrapped in a deep hydrogen atmosphere over a global ocean, could also be habitable, and crucially, that its puffy hydrogen atmosphere would be far easier to read than the thin air of a rocky planet. In other words, if Hyxian worlds exist, they might be both more common and more observable than Earth twins, which would make them some of the best places to search for the chemical signs of life. K218b became the flagship test of that whole idea, the first world where the Hyxian picture could be checked against real data. The reading came in the year 2023, when the James Webb Space Telescope studied the composition of K218b's atmosphere. And what it found was, by itself, a genuine milestone. The telescope confidently detected two gases, methane and carbon dioxide. Just as important was what it did not find. It did not find ammonia. Now, that specific combination, methane and carbon dioxide present, ammonia absent, is not a random result. It is exactly what the models predict for a hydrogen atmosphere sitting on top of a global water ocean. The ammonia, in that scenario, gets dissolved away into the sea below, which is why you see so little of it in the air above. In other words, The chemistry the telescope measured matched the chemistry a Hycean ocean world should have. That result alone would have earned K218b a place in the history of the search for other worlds. But there was something else in the data. Fainter, buried deeper, far more provocative. Alongside the confident detections of methane and carbon dioxide, the telescope registered a tentative fingerprint of a third molecule. Its name is dimethyl sulfide, usually shortened to the three letters DMS. And the reason a whisper of dimethyl sulfide sent a current of quiet electricity through the entire field of astrobiology is because of where that molecule comes from here at home. On Earth, dimethyl sulfide is made almost entirely by living things. It is produced chiefly by marine phytoplankton, the great drifting clouds of microscopic life that fill the sunlit layers of our oceans. When you stand at the shore and breathe in that particular tang, that briny, oceanic smell, part of what you are smelling is dimethyl sulfide, the metabolic exhalation of countless trillions of tiny organisms. It is, quite literally, the smell of life in the sea. And crucially, in the known catalogue of atmospheric chemistry, there was thought to be no strong, ordinary, non-biological way to make dimethyl sulfide in large quantities. On Earth, if you find DMS in the air, you have found the breath of living things. So consider what a detection of dimethyl sulfide in an alien atmosphere would mean. It would mean that we might be reading the metabolic exhaust of an entire ocean of alien life, the collective breath of alien plankton, drifting in a global sea beneath a hydrogen sky, more than 100 light-years away. It would mean that when we looked at K218b, we were not looking at a habitable world. We were looking at an inhabited one. The implication was so large that it is worth slowing down to feel it. We would be smelling life on another world. This is exactly the moment where the discipline of science earns everything it demands of itself, and where this story becomes something better than a headline. Because the people who made the detection were the first to insist on caution. The tentative DMS signal, in that first announcement, was weak. And in 2025, a follow-up observation using a different instrument aboard the same telescope was reported to strengthen the signal, bringing it up to what scientists call a 3 sigma level. Now, 3 sigma sounds impressive, and it is not nothing. It means there is only about a 3 in 1,000 chance that the data would look this way purely by accident. But 3 sigma is not the standard that astronomers require before they will say a thing is real. That standard is 5 sigma, a chance of a fluke smaller than 1 in a million. 3 sigma has fooled scientists before. Signals that strong have appeared, been celebrated, and then quietly evaporated under more data. 3 sigma is a reason to keep looking. It is not a reason to announce that we have company. And the field did exactly what it should. Independent teams took the same data and reanalyzed it, and they raised serious doubts. Some argued that the dimethyl sulfide feature might not be uniquely identifiable at all, that its supposed fingerprint overlaps with the fingerprints of other molecules, so that what looks like DMS could be something else entirely wearing the same mask. Others pointed to a subtler and more stubborn problem, a kind of noise in the data called red noise, a wandering, correlated flicker in the detectors that can, all on its own, sculpt itself into shapes that look like real signals when there is nothing there. A NASA-led study went further, examining the planet and finding no conclusive evidence for dimethyl sulfide, while confirming the world's water-rich nature and the genuine complexity of its atmosphere. The chemistry of K218b is real and fascinating. The plankton is not established. There was even a challenge to the deepest assumption of all. If dimethyl sulfide is only made by life on Earth, then finding it elsewhere points to life elsewhere. But chemists began asking whether that assumption holds. There have been reports of dimethyl sulfide appearing in cometary material, in the cold, lifeless chemistry of comets, which would mean the molecule is not the clean and exclusive signature of biology that it first appeared to be. If DMS can be made without life, even in small amounts, then its presence in an atmosphere is a weaker clue than the first excitement suggested. The research now includes the sober question of whether this so-called biosignature can be forged by chemistry with no living thing anywhere near it. So where does that leave K218b, honestly? The dimethyl sulfide is not confirmed. It may not survive the next round of observations. The signal might dissolve back into the noise it may have come from. And even if the molecule is truly there, it might have a non-living source that strips it of its meaning. This is not a discovery of life. It is important to say that plainly and to keep saying it. What it is something almost stranger and in its way more moving. It is proof of where we now stand. Because think about what the argument actually is. The debate over K218b is not whether it is possible in principle to ever detect life on a distant world. That debate is over. The debate is whether the faint whiff we just caught in the atmosphere of a specific named planet 124 light-years away is real or an artifact. That is an astonishing place for the human species to have arrived. For the entire span of our existence, the question of life beyond Earth was a matter of philosophy, of imagination, of looking up at night and wondering with no way to check. And now it has become a matter of instrument calibration, of exposure times, of whether a 3 sigma feature holds up at 5. We have moved the whole question from impossible to merely uncertain, and that shift, quiet as it is genuinely new to the history of everything. It is worth appreciating just how faint the whole signal is, because that faintness is the source of every difficulty and every doubt. When K218b passes in front of its star, only a razor-thin sliver of starlight grazes through the upper edge of its atmosphere on its way to us, and it is in that sliver that all the chemistry is written. The dimming of the star caused by the planet is tiny, and the additional dimming caused by a single molecule absorbing its particular colors within that sliver is tinier still, a change measured in fractions of a fraction of a percent. To detect a gas like dimethyl sulfide, you are trying to read the faintest of shadows cast by a whisper of atmosphere on a thread of light that has already crossed 124 light-years. That we can do it at all is astonishing. That it is hard and prone to being fooled by noise and easy to disagree about is exactly what you would expect from a measurement pushed to the very limit of what the greatest telescope ever built can achieve. The uncertainty is not a sign that the science is sloppy. It is a sign that we are working right at the edge of the possible. There is also a longer game being played here, beyond this one planet, and it is worth naming. K218b is a test case, a proving ground for the whole enterprise of reading life in the atmospheres of distant worlds. Whatever its final answer turns out to be, the arguments it has provoked about false signals, about red noise, about whether a gas is truly a biosignature, about what standard of proof a claim of life must meet, are sharpening the tools and the standards that will be applied to every world we examine after it. When a future telescope reads the atmosphere of some other planet and finds a gas that looks like life, the caution and the rigor that the field learned on K218b will be what tells us whether to believe it. In that sense, even if the dimethyl sulfide dissolves into noise, K218b will have earned its place in this history, as the world on which humanity learned how carefully it would have to look. The way to settle it is more time on the telescope. Longer exposures, more passes of the planet in front of its star, a slow accumulation of light until the signal either firms into something undeniable or fades into nothing. That work is underway. It will take years. And at the end of it, we will either have a stronger case that something breathes in the ocean of K218b, or we will have learned, once again, how easily hope can carve a face out of noise. Either answer is worth having. Both are the same act of looking carefully at a thing we cannot yet explain. It is worth understanding why the methane and carbon dioxide detection mattered so much, even before the dimethyl sulfide came into it, because that first result is the solid ground the whole debate stands on. For years, the great difficulty in reading small planet atmospheres was that they gave up almost nothing. Telescope after telescope would look at a sub-Neptune and see a flat, featureless spectrum, the sign of a world hidden under thick, high clouds or haze that blocked any view of the gases below. K218b, by contrast, actually showed its chemistry. Methane and carbon dioxide are exactly the pair of molecules that a hydrogen atmosphere over a water ocean should display, and the near absence of ammonia fit the same picture, because ammonia would dissolve into the ocean below. It was a coherent, self-consistent reading of a genuine ocean world, and that alone would have been a landmark. The dimethyl sulfide was the electrifying extra, but the foundation beneath it was already remarkable. The caution that surrounds this planet is not timidity. It is the hard-earned memory of how often hope has run ahead of evidence in exactly this field. The history of the search for life beyond Earth is dotted with announcements that seemed, for a season, to be the moment, and then quietly came apart under scrutiny. A gas detected on one world turned out to be an instrument artifact. A signal from another turned out to be contamination. A claim about a third could not be reproduced by other teams. None of those were failures of honesty. They were the ordinary, necessary process of science testing itself. But they taught the field a deep humility about extraordinary claims, and they are why the people studying K218b, including the very team that first reported the dimethyl sulfide, keep insisting on the word tentative, keep pointing to the missing 5 sigma certainty, keep welcoming the reanalyses that push back. A discovery this large has to survive being attacked from every direction before it can be believed. That is not the enemy of the search. It is the search. There is also genuine disagreement about what kind of world K218b even is, and that uncertainty ripples through everything. The Hycean picture, an ocean under a hydrogen sky, is one interpretation, and a hopeful one, because such a world could be temperate and habitable. But other researchers have argued that the same data could fit a hotter, harsher planet, perhaps one with a magma surface or a gassy envelope with no ocean at all, in which case the chemistry would mean something entirely different, and the question of life would fall away. The planet's true nature is still argued in the literature, and until that is settled, even a confirmed detection of dimethyl sulfide would be hard to interpret cleanly. Everything about K218b, the world, the ocean, the gas, the meaning, sits inside overlapping uncertainties, each waiting on more light. That is what K218b leaves us with. The possible breath of an alien ocean, unproven and impossibly far away, hovering at the edge of what our instruments can hear. It is a fingerprint of life, written in gas, in a place we will never visit, that we can only read as light. But there is another kind of fingerprint of life, and it does not require reading an atmosphere across 100 light-years. It is closer than that. Much closer. The next fingerprint on our list is not a whisper in a distant sky. It is sealed inside a small titanium tube, sitting right now on the surface of Mars. Number 7. The leopard spots. Mars today is a hard place to imagine anything living. It is a freezing desert, its surface bombarded by radiation that no atmosphere is thick enough to stop, its rocks rusted red by ancient chemistry, its air so thin that liquid water cannot survive on the open ground. If you went there now and searched, you would find nothing moving, nothing breathing, nothing that had breathed in a very long time. But Mars was not always this way. Roughly 3.5 billion years ago, it was a genuinely different world. It had blue skies, it had a thicker atmosphere, and it had water, real running water, rivers and lakes and rain, moving across a warmer surface under a younger sun. That lost world left a record, and one of the finest surviving pages of that record is a place called Jezero Crater. Jezero is a basin about 45 kilometers across, punched into the Martian surface by an ancient impact, and long ago it filled with water. A river flowed into it, building a delta as it slowed and dropped its sediment, the same kind of branching, fan-shaped delta that rivers build on Earth where they meet a lake or a sea. For a long stretch of Martian history, Jezero was a lake with a river delta feeding it, exactly the kind of warm, wet, mineral-rich environment where, on Earth, life not only survives, but leaves its traces behind in the rock. That is precisely why it was chosen. In the year 2021, NASA landed the Perseverance rover in Jezero Crater, sent there for one central purpose: to read the rock of an ancient lakebed for any sign of a Martian biosphere that may have lived and died before Earth itself had anything more complicated than microbes. Perseverance is not a simple machine. It carries an array of sophisticated instruments designed to do chemistry and geology on the surface of another planet. Among them is a device that can fire an ultraviolet laser at a rock and map, point by point, the minerals and organic molecules spread across its surface, reading the fine chemical texture of stone that no human hand will touch for decades, if ever. And in July of 2024, that machinery was turned on a particular target. In an ancient river channel, the rover found a reddish mudstone, a rock made of fine sediment laid down in still water long ago. The team gave it a name, as they name everything they study. They called it Oumuamua Falls. And when the rover drilled into it and pulled out a core sample, that sample got a name too. It was called Sapphire Canyon. What was found inside Oumuamua Falls became, more than a year later, in a careful announcement in September of 2025, the strongest thing the mission has ever produced. NASA used a very particular phrase, chosen with great care, weighed word by word. They called it a potential biosignature. To understand what that means, you have to look at what the rock actually contains. The surface of Oumuamua Falls is dotted with small features that the team described in plain, almost homely language. There are tiny dark marks they call poppy seeds, and slightly larger pale-rimmed spots they call leopard spots, each only millimeters across, scattered through the stone. And tangled up with these spots, woven right through the same rock, is organic carbon, the carbon-based molecules that are the raw material of all life we know. But organic carbon by itself is not proof of anything. Organic molecules can form without life, through ordinary geology, through volcanic chemistry, delivered by falling meteorites. The carbon alone was interesting, not conclusive. What made the rock extraordinary was what the instruments found inside the spots. Within the leopard spots and their dark rims, the rover's chemistry identified two specific minerals. One is called vivianite, a hydrated iron phosphate, a mineral of iron, phosphorus, and water. The other is called greigite, an iron sulfide, a mineral of iron and sulfur. And here is why that pairing made scientists lean in. On Earth, these exact minerals, vivianite and greigite, are frequently produced by microbes. Certain microorganisms make their living through what are called electron transfer reactions, pulling energy out of sediment by shuffling electrons between molecules, feeding on organic matter, and using elements like sulfur and phosphorus in the process. And a well-known byproduct of that kind of microbial metabolism is precisely these kinds of minerals, formed in precisely these kinds of patterns. The pattern in the Martian rock, the spots, The rims, the mineral pairing, the entangled organic carbon looks like the pattern that living things leave behind in mud on Earth. It is worth understanding what organic carbon does and does not tell us, because the distinction runs through this entire discovery. The word organic in chemistry does not mean living. It simply means a molecule built around carbon, and such molecules can be made by life, but they can also be made without it, by volcanic processes, by reactions in water and rock, or delivered ready-made by the meteorites that constantly rain onto every world. Perseverance has found organic molecules at several sites in Jezero, and on its own that finding, while important, does not point to biology, because the ingredients of life are not the same as life. What lifted Cheyava Falls above the ordinary was not the organic carbon alone. It was the organic carbon found in intimate association with the specific minerals, vivianite and gragite, arranged in the specific leopard-spot patterns that, on Earth, microbial metabolism produces. It is the combination, the carbon and the minerals and the pattern all tangled together in the right way, that made the rock a potential biosignature rather than just another interesting stone. The words matter enormously, and this is where the whole discovery lives or falls. A potential biosignature does not mean life has been found. It does not mean Perseverance discovered Martian microbes. It means something narrower and more honest. It means the sample shows a feature that biology is known to create, in a setting where biology could plausibly have lived, without any confirmed non-living explanation ruling it out. Those are three separate conditions, and all three are met. But there is a fourth thing that is not met, and it is decisive. The same minerals, the same textures, the same patterns can, in principle, also form through purely chemical reactions with no life involved at all. Iron and sulfur and phosphorus can arrange themselves this way through ordinary chemistry under the right conditions, given enough time. And so the Mars result is suggestive, not decisive. It resembles what biology leaves behind. But resemblance is not proof. A thing that looks like a footprint is not always a foot. This is the honest and slightly agonizing truth of Cheyava Falls. It is the best evidence for ancient life on Mars that has ever been found, and it is not enough. And the reason it is not enough is a limitation that no rover can overcome, no matter how clever. The instruments that Perseverance can carry, the lasers and spectrometers small enough and rugged enough to survive the journey and function on the Martian surface, simply cannot do the kind of definitive analysis that would settle the question. To truly know whether those leopard spots were made by life or by cold chemistry, you would need the full weight of Earth's laboratories, the electron microscopes and mass spectrometers, and delicate, patient tests that fill entire buildings and cannot be flown to Mars. The answer, if it exists, is locked in a fineness of detail that only Earth can read. And so Perseverance did the one thing it could. It sealed the sample. Sapphire Canyon, along with the rover's other precious cores, has been sealed into a sterile titanium tube, protected from contamination, protected from the Martian environment, waiting. There is a plan, an ambitious and difficult and not yet guaranteed plan, to send another mission to Mars, retrieve those tubes, and fly them home. If that campaign succeeds, the sealed Martian rock would face every test that human science can devise, and the question that has hung over Mars for more than a century might finally have an answer. But that campaign faces enormous challenges of cost and engineering and time, and it has not happened yet. Until it does, the leopard spots sit exactly where they are. Think about that, because it is one of the strangest situations in the whole of exploration. The single rock that might tell us we were never the only living world, the physical object that could carry the answer to the oldest question, has already been found. It has already been drilled. It has already been sealed into its tube. It is not somewhere out in the dark, undiscovered. It is sitting on the surface of Mars, catalogued and waiting, a finished piece of evidence in an unfinished investigation. The only thing standing between us and the answer is the trip home. The distance between our species and one of the largest facts it could ever learn is, right now, a problem of transportation. It is worth lingering on the setting because the place where the leopard spots were found is as important as the spots themselves. Jezero crater was not chosen at random. It was selected precisely because orbiting spacecraft had already spotted, from above, the unmistakable shape of an ancient river delta spilling into the basin, a fan of sediment laid down where a river once slowed and dropped its load into a standing lake. On Earth, river deltas are among the finest places to preserve traces of life, because the fine muds that settle there entomb organic material gently and lock it away from the destructive forces that would otherwise erase it. A delta on Earth is where you would go to look for the record of ancient microbes, and so a delta on Mars, preserved for 3.5 billion years in a cold, dry, stable environment, is one of the best places in the entire solar system to search for the record of a Martian biosphere, if one ever existed. Perseverance was sent to exactly the kind of place where the answer, if there is one, would most likely be kept. And it is worth sitting, just for a moment, with what the two possible answers would mean, because the stakes are larger than a single rock. If the leopard spots are eventually shown to be the trace of ancient Martian life, and if that life arose independently of life on Earth, then we would have learned something profound, that life began separately on two neighboring worlds in the same solar system. That would suggest, powerfully, that life is not a fluke, not a one-in-a-universe accident, but something that tends to happen wherever the conditions allow, which would mean the universe is very likely full of it. On the other hand, if the spots turn out to be the product of ordinary chemistry, with no life involved, then we would have learned something humbling, but also valuable, that a warm, wet, mineral-rich world can build patterns that look like life, without any life at all, and that we must be more careful still about what we take as proof. Either answer, when it finally comes, would reshape how we think about our place in the cosmos. And both of them are waiting, right now, in a sealed tube on the floor of an empty crater. There are deeper uncertainties still, waiting behind the first one. Even if the leopard spots turn out to be biological, even if that rock holds the trace of ancient Martian microbes, there would be a further question, and it is a profound one. Was that Martian life independent from life on Earth, a completely separate origin, a second genesis that would tell us life is easy and the universe is probably full of it? Or did the two worlds share a beginning? Life started on one and carried to the other on the meteorites that impacts have traded back and forth between Mars and Earth across billions of years. A shared origin would be its own kind of revelation, but a lonelier one. An independent origin would change everything. And all of it hangs on a sample already collected, already sealed, already waiting on a cold red world for a ride that has not yet been built. To feel the weight of the September 2025 announcement, it helps to remember that this is not the first time Mars has seemed to whisper the word life. Nearly 30 years earlier, in the 1990s, a meteorite from Mars, found in Antarctica, made headlines around the world when a research team reported tiny structures inside it that resembled fossilized microbes, along with chemical hints that some read as signs of biology. The announcement was so significant that it was spoken of at the highest levels of government, and it helped launch the entire modern field of astrobiology and drove the creation of the very rover programs that put Perseverance on Mars. But in the decades that followed, as scientists examined that meteorite from every angle, the consensus swung toward caution. Most researchers came to believe that the structures and chemistry could be explained without life, by ordinary geology and by the violence of the impact that launched the rock into space. The lesson of that episode hangs over Shayava Falls. Mars has looked like it was about to answer before, and the answer dissolved. That memory is exactly why NASA weighed the words potential biosignature so carefully this time. The instruments that read the leopard spots are worth naming because the discovery is only as good as the machinery behind it. Perseverance carries a device that fires an ultraviolet laser at a rock and maps where organic molecules and minerals sit across its surface, revealing not just what is present, but how it is arranged, which spots hold which chemistry. It carries another instrument that can determine the precise elemental makeup of a target, down to the scale of a grain of salt, building a fine chemical map of the stone. It was these tools, working together on the surface of another planet, that found the vivianite and the greigite nested in the leopard spots, tangled with organic carbon in exactly the spatial relationship that microbial chemistry would produce. That is a remarkable thing for a machine the size of a car to accomplish, tens of millions of kilometers from the nearest laboratory. But it is also precisely the limit. The rover can find the pattern. It cannot perform the exhaustive, molecule-by-molecule tests that would prove the pattern was made by life rather than mimicked by chemistry. The plan to bring the samples home is one of the most ambitious undertakings ever proposed in the exploration of the solar system, and its difficulty is part of the story. To return Sapphire Canyon to Earth would require sending another spacecraft to Mars, landing near the cached tubes, retrieving them, launching them off the surface of Mars, the first launch ever attempted from another planet, rendezvousing with a return vehicle in Mars orbit, and flying the whole precious cargo back across the solar system to a careful landing on Earth. Every step is hard. The campaign has faced questions of cost and schedule and engineering, and it has not yet been carried out. And so the strangeness of the situation deepens the longer it goes on. The evidence is already collected. The answer may already be sealed in that tube. And the only thing standing between the human species and one of the largest facts it could ever learn is the enormous, unfinished problem of going back to get it. That is what Shayava Falls leaves us with. The traces that life leaves behind, sitting sealed on the surface of Mars, suggestive and unfinished, one sentence short of an answer. Up to this point, every discovery on our list has been about the same underlying question, whether something out there ever lived. But from here, the list turns. Because as we descend past number 7, the discoveries stop being about whether something lived and start being about something stranger and more specific. They start being about whether something was built. Number 6, the stars that glowed wrong. In the year 1960, a physicist named Freeman Dyson published a short paper that carried an idea far larger than its length. Dyson was thinking about energy and about growth. He reasoned that any civilization that kept expanding, kept building, kept using more and more power over the centuries would eventually run into a simple wall. A planet catches only a tiny fraction of the light its star pours out. The rest of that light streams past into empty space and is lost forever. A truly advanced civilization hungry for energy would look at that waste and want to capture it. And the logical place to go for more power is not the planet. It is the star itself. Dyson imagined that such a civilization might surround its sun with an enormous swarm of collectors, an immense fleet of structures spread around the star to catch a large share of the light it produces. This idea has been drawn many times since as a solid shell, a smooth sphere enclosing a star, but that is not really what Dyson meant, and a solid shell would not even be stable. He meant a swarm, countless separate collectors in countless separate orbits, together intercepting a meaningful fraction of a star's total output. The scale of such a thing is almost impossible to hold in the mind. It would be engineering carried out on the scale of a solar system, the harnessing of an entire star. But the truly important part of Dyson's paper was not the megastructure. It was the consequence he pointed out for us, the watchers. Because energy does not simply vanish when it is used. The light that those collectors capture would be put to work, and then, by the unbreakable laws of thermodynamics, it would be released again as waste heat. Not as visible light, but as heat, in the infrared, the long invisible wavelengths that our own bodies give off. That warm ground radiates on a cool evening. So a star wrapped in machinery would look wrong in a very specific and detectable way. It would appear dimmer than it should in ordinary visible light because much of that light was being intercepted. And it would appear unexpectedly bright in the infrared, glowing with the re-radiated waste heat of everything the collectors had absorbed. Dimmer where it should be bright, and glowing where it should be dark. Here is what made Dyson's paper more than science fiction. His real proposal was not to build such a thing. It was to look for one. He was suggesting a search. If any civilization anywhere in the galaxy had wrapped its star in collectors, then the signature would be written across the sky in infrared light, waiting to be found by anyone who thought to look for a star glowing wrong in exactly that way. He had turned the largest imaginable engineering project into an observational test. You do not have to imagine the aliens. You just have to search the sky for the heat. For decades, that search remained mostly a thought experiment. Astronomers knew the idea, and now and then someone would sift through infrared data looking for candidates, but there was no systematic, dedicated hunt through the modern all-sky surveys. Then, in the year 2024, a project named Hephaistos did the search properly and at scale. Hephaistos was named for the Greek god of the forge, the maker of divine machinery, and its goal was exactly what Dyson had described 60 years earlier. Its method was to combine data from 3 of the great sky surveys humanity has built. The first was Gaia, the European star mapping mission that has measured the precise positions, distances, and brightnesses of well over 1 billion stars. The second was the 2-micron all-sky survey, which mapped the entire sky in near-infrared light. And the third was WISE, the Wide-Field Infrared Survey Explorer, a space telescope that scanned the whole sky in the mid-infrared, in exactly the wavelengths where Dyson's waste heat would shine. By combining these 3, the Hephaistos team could do something powerful. They could take a star, know its true distance and brightness and type from Gaia, predict exactly how much infrared light it ought to naturally produce, and then check the actual infrared measurements to see whether the star was glowing with more heat than it should. Any star with a genuine, unexplained excess of mid-infrared light, an excess consistent with a warm shell of material at a temperature somewhere between 100 and 300 Kelvin, would be flagged. That temperature range is not arbitrary. It is roughly the range you would expect for a structure orbiting a star at a comfortable distance, warmed by the star, but not roasted, radiating gently in the infrared. It is, in other words, the temperature a Dyson swarm might plausibly have. The team searched roughly 5 million stars. 5 million. And out of those 5 million, after all the ordinary explanations had been accounted for, they were left with 7. 7 stars, all of them small red dwarfs, each one showing more infrared glow than a bare star of its kind should produce, each one consistent with that telltale warm shell temperature. 7 candidates, out of 5 million, for the single most consequential object in the history of astronomy. Let me put you at the moment of that result, because it is not what you might imagine. You are looking at a table of numbers. Not a photograph of a glowing ring around a star, not a beam of light, not a message. A spreadsheet. 5 million rows have been narrowed down to 7, and those 7 rows sit there on the screen, quiet and undramatic. Each row is a real star, with a real catalog designation, a string of letters and digits that stands for an actual point of light in an actual patch of the southern or northern sky. Each of these stars is a genuine red dwarf, burning steadily, tens or hundreds of light years away. And each one is putting out more heat than it has any right to. You can check the math again. You can pull the measurements from 3 separate telescopes and lay them side by side. The excess is there. 7 small stars, glowing wrong in the infrared, refusing to resolve into anything ordinary. There is no fanfare in the room. There is only the strange, heavy quiet of a question mark that will not go away, and the knowledge, sitting there in a column of numbers, that if even one of these 7 turned out to be what Dyson had imagined, it would be the largest fact human beings had ever learned. And it would have arrived, not as a signal, not as a voice, but as a faint reddish excess in a table. This is exactly why the search has to be done carefully, and it is exactly why this entry belongs on a list of the strangest discoveries rather than in a tabloid. Because almost immediately, other astronomers proposed a mundane and deflating explanation, and they were right to. The problem is contamination. There is a particular kind of distant galaxy, called a hot, dust-obscured galaxy, that astronomers have nicknamed a hot DOG. These galaxies are dim in visible light because thick dust hides them, but they blaze fiercely in the infrared, glowing with the heat of that dust, warmed by intense activity at their cores. Now imagine one of those infrared bright galaxies sitting, by pure chance, almost exactly behind one of these red dwarf stars from our line of sight. In the infrared images, the light of the star and the light of the hidden galaxy would blur together into a single measurement. The galaxy's fierce infrared glow would contaminate the star's reading, and the combination would look, to our instruments, exactly like a star with a mysterious infrared excess. Exactly like a Dyson candidate. The analyses came quickly. Researchers calculated the density of these background galaxies across the sky and argued that such chance alignments could plausibly account for the infrared excess in the candidates, perhaps in all 7 of them. And then came the test that matters most, the one that separates a real search from an endless argument. The James Webb Space Telescope, the sharpest infrared eye ever built, was pointed at 2 of the candidates. And it resolved the picture. For those 2 stars, the excess infrared light was not coming from the star at all. It was coming from faint background galaxies sitting within about 1 arcsecond of the star, an angle so small it is a tiny fraction of the width of a full moon, close enough that the older, blurrier surveys had smeared the 2 together. One of those background galaxies was itself a hot, dust-obscured galaxy, exactly the kind of contaminant the skeptics had predicted. The candidates, on close inspection, were dissolving into distant galaxies caught in the same pixel. There is a genuine elegance in how the contamination was caught, and it rewards a moment's attention because it shows science self-correcting at its best. The skeptics did not simply assert that background galaxies were to blame, they made a prediction. They said that if contamination was the cause, then a sharper instrument, one able to separate the star from anything lurking behind it, should reveal a distinct background source at the position of the excess. That is a testable claim, and it was tested. The James Webb Space Telescope, with its far finer vision, looked and found exactly what the prediction required: faint galaxies sitting just behind the candidate stars, glowing in the infrared. A hypothesis was raised. It made a specific prediction. The prediction was checked with a better instrument, and it held. That is not a disappointment. That is the machinery of honest inquiry, working precisely as it should, and it is worth admiring even though the answer it delivered was the deflating one. So the leading explanation now is not alien engineering. It is background galaxies, faint and far away, contaminating the light of ordinary red dwarf stars. That is where the honest weight of the evidence sits, and it should be said plainly rather than dodged. We almost certainly did not find a Dyson sphere. And yet this entry earns its place, and it earns it for a reason that is easy to miss if you only want the dramatic answer. The case is not fully closed for every candidate, And more importantly, the story is exactly what a real techno-signature search looks like. It is not a movie. It is a slow, adversarial, unglamorous process. Someone proposes a search. The search flags candidates. Skeptics propose a boring explanation. Sharper instruments test it. Most candidates fall. That is not failure. That is the method working exactly as it should, and the value of Hephaistos is not that it succeeded in finding aliens. It is that it made the search real, because that is genuinely new. For 60 years, Dyson's idea sat mostly in the territory of the hypothetical, a clever suggestion that everyone knew about and few pursued systematically. Now a team has actually done it. They have taken a survey of 5 million stars, applied Dyson's exact test, produced candidates, and subjected those candidates to rigorous follow-up. The infrastructure now exists. The method is proven, and the next generation of infrared surveys will flag far more stars, and the process will run again and again, sharper each time. The honest answer to the question, is anyone out there building, is not a triumphant yes. It is not that we can prove, not yet. But the looking has begun in earnest, and it is being done well. There remain open questions, and they are worth naming. It is not certain that every one of the 7 candidates is fully explained by background contamination, because only some have received the full resolving follow-up. And the deeper question of how the contamination problem scales as future surveys flag thousands of new candidates is unsolved. Each new candidate will demand the same patient testing that these 7 received. The search is not finished. It has only, finally, properly started. It is worth being concrete about what the 7 candidates actually were, because the specifics matter to the story. All 7 were red dwarf stars, small and cool and dim, the most common kind of star in the galaxy. Each one showed an excess of mid-infrared light, more heat than a bare star of its type ought to produce, and the amount of that excess pointed to a source with a temperature somewhere in the range of 100 to 300 Kelvin, which is roughly the warmth you would expect from a shell of material orbiting at a comfortable distance from the star, warmed but not scorched. In 3 of the 7 cases, the candidates were also matched with radio sources detected in sky surveys, which only deepened the intrigue at first. 7 stars, drawn from 5 million, each glowing with the specific kind of excess heat that Dyson had predicted a star-enclosing swarm would radiate. On the face of it, before the follow-up work, it was exactly the result the search had been built to find. The reason the contamination explanation is so persuasive comes down to a matter of angular scale, and it is worth making that concrete. The older infrared surveys that first flagged these stars have relatively coarse vision. They cannot always separate 2 sources that lie very close together on the sky, and so the light from a star and the light from something almost directly behind it can blur into a single blended measurement. A hot, dust-obscured galaxy, blazing in the infrared but far too distant and faint to notice in ordinary light, could sit within a tiny fraction of the width of the full moon behind one of these red dwarfs, and the coarse survey would smear the 2 together into what looks like a single star with a mysterious infrared glow. When a far sharper instrument, the James Webb Space Telescope, was pointed at 2 of the candidates, it could resolve what the older surveys could not, and it found exactly that, faint background galaxies hiding within about 1 arcsecond of the stars, one of them confirmed to be precisely the kind of hot, dust-obscured galaxy the skeptics had predicted. The infrared excess was real. It just was not coming from the star. To understand why anyone takes the idea of a star-enclosing structure seriously enough to search for it, it helps to know the framework Dyson's thinking sits inside. A few years after his paper, a Soviet astronomer named Nikolai Kardashev proposed a way of ranking civilizations by the sheer amount of energy they command. A civilization of the first kind harnesses the energy available on its own planet. A civilization of the second kind harnesses the entire energy output of its star. A civilization of the third kind commands the energy of a whole galaxy. It is a simple ladder, and it is entirely hypothetical, but it makes a serious point. If technological civilizations tend to grow their energy use over time, then some of them, somewhere, given enough time, might climb toward that second rung, learning to capture the output of their sun. And a civilization on that rung is exactly what Dyson described, and exactly what leaves the infrared signature his search was designed to catch. The Dyson sphere is not a random fantasy. It is the specific, physical thing that the energy hunger of a long-lived civilization would tend to produce. There were smaller searches before Hephaestus, and they are worth acknowledging because they show this is a genuine scientific tradition and not a sudden whim. Over the decades since Dyson's paper, various astronomers combed through infrared survey data, looking for stars with the telltale excess heat, checking catalogs, flagging oddities, mostly finding dusty stars and other natural explanations. None found a convincing candidate, but each refined the method and narrowed the possibilities. What made Hephaestus different was the sheer scale and quality of the modern data, the ability to combine 3 great surveys, to know each star's true distance and type with precision, and to sift 5 million stars systematically rather than checking a handful. The search got better because the maps of the sky got better. That is how this kind of work advances, not in a single dramatic discovery, but in the steady sharpening of what we can rule out. It is worth sitting for a moment with the sheer scale of what would have to be true for even one candidate to be real, because it puts the whole search in perspective. To build a structure that captures a meaningful fraction of a star's light would require an amount of material and an amount of engineering that dwarfs anything our species has ever attempted by factors almost too large to write down. It would mean disassembling planets, moving matter on the scale of worlds, sustaining a project across timescales far longer than all of recorded human history. When we search for a Dyson signature, we are not searching for a slightly more advanced version of ourselves. We are searching for the fingerprint of a civilization so far beyond us that its everyday engineering would look, to us, like the reshaping of a solar system. That such a thing might exist is not impossible under the laws of physics. And the fact that we can now scan 5 million stars asking whether any of them shows the sign of it is, in its own quiet way, one of the strangest capabilities our species has ever developed. That is what the Dyson search leaves us with. We built the thing Dyson asked for, aimed it at 5 million suns, and learned that the honest answer to whether anyone is out there building is not yet. Not that we can prove, but that the search is now real and running. And notice the quiet lesson buried in that result. A star can glow wrong because of what surrounds it, because of light from something else blurred into its own. That was the whole story here. But the next star on our list glows wrong for a completely different reason. It does not glow wrong because of anything around it. It glows wrong because of what is inside it. Number 5. The star that should not exist. We are halfway down the list now, and it is worth pausing for a moment to look back at the ground we have crossed. We began gently, with chemistry that could cradle life. We stood on the shore of a methane sea on Titan, where the ingredients for a membrane without water fall from the sky by the ton. We looked at LHS 1140b and found a rocky world with a nitrogen atmosphere and, quite possibly, an ocean staring out at its star like a single blue eye. We caught the faint, contested breath of an alien ocean at K218b, a gas that here on Earth only life is known to make. And we drilled the leopard spots on Mars, the traces that biology leaves behind, sealed now in a tube and waiting for a ride home. Then the list turned. We stood in front of 7 stars that glowed wrong in the infrared. The first place we stopped asking whether something could live and started asking whether something had been built. From here, as we descend toward number 1, the discoveries stop being about places that could hold life at all. They become things we simply cannot explain. And the first of them is a single star, 1,000 light-years away, whose light breaks the rules of how stars are allowed to be made. In the year 1961, a Polish-Australian astronomer named Antoni Przybylski was working at the Mount Stromlo Observatory in Australia, studying the light of stars. He turned his instruments toward a star in the southern constellation of Centaurus, catalogued as HD 101,065, about 1,000 light-years from Earth. And when he spread its light out into a spectrum, he found something that made no sense. To understand why, you have to understand what a spectrum is, because it is one of the most powerful tools in all of science. When you pass a star's light through an instrument that separates it into its component colors, you do not get a smooth rainbow. You get a rainbow crossed by dark lines, narrow gaps where specific colors are missing. Each of those dark lines is a fingerprint. Every element in the universe, every kind of atom, absorbs its own particular set of colors, and so the pattern of dark lines in a star's spectrum tells you precisely and unmistakably which elements are present in that star's outer layers. A spectrum is a chemical inventory written in shadow, readable across 1,000 light-years. It is how we know what the stars are made of without ever touching one. When Przybylski read the spectrum of his star, the inventory was wrong. In a normal star, like our Sun, the spectrum is dominated by the fingerprints of common elements, above all iron and nickel, the ordinary metals that stars forge and carry in abundance. But in the spectrum of HD 101,065, iron and nickel were strangely faint, far weaker than they should be. And in their place, the spectrum was crowded, flooded, overwhelmed with the fingerprints of rare earth elements: strontium, holmium, europium, a whole crowd of the heaviest and most exotic elements on the periodic table, present at levels that no ordinary theory of how stars work could easily explain. It was as if someone had taken the normal recipe for a star, removed most of the common metals, and stirred in a fortune of the rarest elements in the cosmos. No other star known showed anything quite like it. It came to be called simply Przybylski's star, and it remains one of the strangest single objects in the sky. It is worth understanding just how unusual it is for a star's basic chemistry to be a genuine mystery, because stars are, in most respects, the best understood objects in all of astronomy. We know how they form, how they burn, how they age and die. We can predict with great accuracy what elements a star of a given mass and age should contain, because we understand the nuclear furnaces at their cores and the way they mix and forge material over their lives. The overwhelming majority of stars fit those predictions comfortably. Their spectra show the expected elements in the expected proportions, iron and nickel and the common metals dominating, the rare earths present only in traces. That is the rule, confirmed across countless stars. Przybylski's star is one of the sharpest exceptions ever found to that rule, a star whose surface chemistry is so far from the expected that for decades after its discovery, no one could fully account for it, and in the details, no one fully can even now. The chemistry only grew stranger the harder people looked. Over the decades that followed, as instruments improved and astronomers returned to that crowded, tangled spectrum again and again, some analyses reported signs of elements that have no business being in a star at all. They reported the fingerprints of short-lived radioactive elements, the actinides, elements like technetium and promethium, and in some contested readings, traces of elements from the very far end of the periodic table, the heavy, unstable, fleeting elements that barely exist in nature. And this is where the strangeness sharpens into a genuine problem, because of a simple fact about radioactivity. Some of these elements have half-lives that are, by the standards of a star, almost nothing. The half-life is the time it takes for half of a sample of a radioactive element to decay away. For some of the actinides reportedly seen in this star, that half-life is only thousands or millions of years. That sounds long to a human being, but a star lives for billions of years, and to a star, a few million years is the blink of an eye. An element with a half-life of a few thousand years should have decayed away almost as soon as it formed, vanishing long before we ever looked. To see such elements in the star's atmosphere now, glowing in its spectrum, means one of two things. Either those elements are being produced or delivered continuously, replenished by some ongoing process we do not understand, so that they never get the chance to fully disappear. Or our readings of that impossibly crowded spectrum are being fooled, and the lines we think we see are not really the elements we think they are. There is a mainstream explanation, and it is very likely the right one, so let us give it its due. Przybylski's star is an extreme example of what astronomers call a chemically peculiar star. In certain stars, ones with unusually calm, stable outer atmospheres and strong magnetic fields, a process called diffusion can take hold. Without churning and mixing, some elements slowly sink under gravity, while others are gently pushed upward by the pressure of the star's own light, floating up and concentrating in the thin, visible layers where we read the spectrum. In such a star, the surface chemistry can look wildly unrepresentative of what the star is actually made of, enriched in certain elements far beyond their true abundance. Przybylski's star is the prototype of a class called rapidly oscillating peculiar A stars, and it even pulses gently, brightening and dimming on a rhythm of roughly 12 minutes. So the impossible-looking spectrum may be a kind of illusion, a real but misleading concentration of certain elements floated up into view by a quiet, magnetic, stratified atmosphere. That is the leading answer, and it should not be waved away. But the reported presence of those apparently short-lived elements has kept stranger ideas alive at the edges of the discussion, precisely because the ordinary explanation has not fully closed the case. One line of speculation, still within the bounds of physics, asks whether the star sits near what theorists call an island of stability. There is a long-standing prediction that certain super-heavy elements, ones far beyond the naturally occurring end of the periodic table, might, at particular combinations of protons and neutrons, be far more stable than their neighbors, surviving for much longer than the fleeting instant most super-heavy elements manage. If such elements existed in Przybylski's star, their slow decay could, in principle, seed the spectrum with the daughter products we struggle to explain. It is an idea about exotic but natural chemistry, and it remains unproven. And then there is the more provocative idea, the one that keeps this star on a list like ours. It is raised, always, precisely because the chemistry is so hard to account for, and it is always labeled for exactly what it is, which is speculation with no evidence behind it. The idea asks a simple, unsettling question. If a technological civilization existed around such a star, and if it disposed of its nuclear waste by dropping it into its own sun, the way we might one day be tempted to dispose of dangerous material, then that waste, the heavy radioactive elements and their decay products, would paint the star's spectrum with exactly the kind of impossible signature we see. The heaviest, deadliest entries on the periodic table showing up in a star's light because someone put them there. It is important to be completely clear. There is no evidence for this. It is not a theory in any serious sense. It is a what-if, raised only because the natural explanations have not entirely settled the matter, and it survives on the strength of the mystery rather than any support of its own. The honest status of Przybylski's star, then, is this. It is very probably a chemically peculiar star. its bizarre spectrum the product of natural processes floating rare elements into view. But the reported short-lived elements are genuinely difficult to explain, and it is not fully certain whether those detections are real or whether they are misreadings of a spectrum so crowded that it defeats our instruments. Two open questions sit at its heart. Whether those actinide lines are true detections or illusions born of an impossibly tangled spectrum. And if they are real, what physical process could possibly replenish elements that should have decayed away long ago? It is worth dwelling on the mechanism that mainstream astronomers favor, because it is genuinely elegant, and understanding it makes the star less magical without making it less interesting. In most stars, the outer layers churn and boil constantly, a roiling convection that keeps everything mixed, so the surface chemistry reflects the whole. But in certain stars, the outer atmosphere is unusually calm and still, and threaded through with a strong magnetic field that suppresses the churning. In that quiet, a slow sorting can take place. Gravity pulls some elements gently downward, while the outward pressure of the star's own light lifts others upward, floating specific atoms up into the thin, visible layers where we read the spectrum. The result is a surface that is wildly unrepresentative of the star as a whole, enriched 100-fold or more in particular elements that have been levitated into view. Przybylski's star is the extreme prototype of this behavior, and its gentle 12-minute pulsation is part of the same picture, the ringing of a stable, magnetic, stratified atmosphere. So the impossible spectrum may be a real effect of a real and understood process, just carried to an extreme we see nowhere else. But the elegance of that explanation does not, by itself, dispose of the hardest detail, and that is why the star keeps its place here. Floating elements upward can concentrate what is already present in the star. It cannot easily manufacture elements that should not be there at all. If the reported traces of short-lived radioactive elements are real, then no amount of levitation explains them, because those elements should have decayed to nothing long before we looked, no matter where in the star they sit. That is the stubborn knot. The diffusion picture beautifully explains the flood of rare earths, the faint iron, the crowded spectrum. It does not obviously explain a signature of elements with half-lives shorter than the blink of a stellar eye. And so the debate turns, in the end, on a question of measurement, on whether those actinide lines are truly there, buried in a spectrum so dense with overlapping features that reading it is like trying to hear one voice in a stadium. Some analysts see the lines clearly. Others suspect they are artifacts of that overwhelming crowding. The instruments have improved, and still the question has not fully closed. The gentle pulsation of the star is worth pausing on, because it connects the strangeness of its chemistry to a whole class of well-studied objects, and shows that Przybylski's star is not entirely alone. It belongs to a family of stars, the peculiar A-type stars, whose calm, magnetic, chemically sorted atmospheres make them oddballs in their surface composition. A subset of these, including Przybylski's star, also pulse rapidly, ringing like bells on rhythms of a few minutes, brightening and dimming ever so slightly as waves ripple through their outer layers. Przybylski's star pulses on a rhythm of roughly 12 minutes, and it is in fact the prototype of that pulsating subclass, the first and most famous example. Studying those pulsations lets astronomers probe the inside of the star, the way listening to a bell tells you about its shape and material, and everything about those studies is consistent with a calm, magnetic, stratified atmosphere, exactly the kind of environment that could float rare elements into view. So the star fits a known pattern in almost every respect. It is only in the extremity of its chemistry, and in those contested traces of elements that should not endure, that it steps outside what the pattern can comfortably explain. There is a reason a star like this attracts the boldest speculation, despite the good, ordinary explanation, and it is worth naming plainly rather than pretending the speculation does not exist. When a phenomenon is almost fully explained, but a small, hard residue resists, the human imagination tends to rush into that residue with the largest ideas it has. The residue here is the reported presence of short-lived elements, and the largest idea available is that something, someone, is putting them there. That is why the waste disposal notion gets attached to this star and not to the thousands of other chemically peculiar stars we know. It is not because there is any evidence for it. It is because Przybylski's star has a genuine loose thread, and loose threads invite pulling. The responsible thing is to hold both truths at once. The mainstream explanation is very probably correct, and the star is very probably a natural, if extreme, chemically peculiar object. And also, honestly, the loose thread has not been fully tied off, which is exactly why it can still be found on a list of the strangest things in the sky. It is a strange thing to realize that after more than 60 years of study, a single ordinary-seeming star, not particularly bright, not particularly close, remains genuinely unexplained in the details of its own light. Przybylski's star is not a distant galaxy or an exotic black hole. It is a star, the most basic and best understood kind of object in astronomy, and we cannot fully account for what its spectrum shows. That should be a little humbling. We have mapped the large-scale structure of the universe and traced its history back nearly to the beginning, and yet here is one star, 1,000 light-years away, quietly refusing to fit the rules, holding on to a secret in the pattern of its light that we have not been able to pry loose. That is what this star leaves us with, a single point of light 1,000 light-years off that still refuses to fit any rule we have written for how stars are allowed to be made. The discomfort of that is not a weakness. It is an honest measure of how much we still do not know, even about something as apparently simple as the light of one star. But Przybylski's star breaks the rules of chemistry. Its light is impossible in the sense that its ingredients should not be there. The next star on our list breaks a different rule entirely. Its ingredients are ordinary. What is impossible about it is written not in chemistry but in time. Because that star, watched across 100 years of photographs, appears to have been quietly, steadily going out. Number 4. The star that faded for a century. About 1,400 light-years from here, in the constellation Cygnus, the Swan, there is an ordinary-looking star with an extraordinary reputation. Its catalogue name is KIC 8462852, but the world came to know it by a friendlier name, Tabby's star, after the astronomer Tabetha Boyajian, who led the team that first tried to explain it. It became, for a while, the most talked-about single star in the entire sky, the subject of headlines and hopes, and one of the most careful scientific investigations of the decade. And it earned all of that attention by doing something that no other star in its part of the sky did. It flickered in a way that broke every expectation. To understand why, you have to understand how astronomers had been watching it. From 2009 onward, NASA's Kepler Space Telescope stared at a single patch of sky containing well over 100,000 stars, measuring their brightness continuously, watching for the tiny, regular dips that happen when a planet crosses in front of its star. Those planetary dips are small and orderly. A planet blocks a fraction of a percent of the star's light, and it does so on a strict schedule, once every orbit, producing a shallow, symmetric, repeating notch in the brightness. Kepler found thousands of planets this way. And the sheer volume of data was so large that some of it was reviewed by ordinary people, volunteers taking part in a public science project, scanning the light curves that automated software had flagged as strange. It was these volunteers, these citizen scientists, who first noticed that something was deeply wrong with Tabby's star. Because Tabby's star did not dip like a planet. It dipped like nothing anyone had seen. Its brightness dropped by enormous amounts, in some events by as much as 22%. Let that number sit for a moment. A large planet passing in front of its star blocks perhaps 1% of the light. This star was losing more than a fifth of its brightness in a single event. And the dips were not regular. They did not repeat on a clean schedule. They arrived at unpredictable times, lasted for varying lengths, and had jagged, complicated, asymmetric shapes that matched no known pattern. Something enormous, or many somethings, were passing in front of that star, blocking huge and irregular fractions of its light, and nothing in the standard catalogue of astronomical objects fit. When Boyajian and her team published the star in 2015, in a paper whose title asked, in effect, "Where is the flux?" meaning, "Where has the light gone?" they had already done the essential work. They had gone through the ordinary explanations one by one and found each one wanting. A single large planet, far too small to block that much light, and the dips were the wrong shape. A cloud of dust or debris. A warm cloud of dust close to the star should glow in the infrared, and the early data did not show the expected infrared excess that such a cloud would produce. Instrument error, the signal held up. Every conventional answer had a problem. And it was precisely that absence of a clean, natural explanation that led an astronomer named Jason Wright to raise, carefully and in the formal scientific literature, the possibility that simply had to be named. He suggested that the strange, deep, irregular dips could be consistent with a swarm of enormous structures in orbit around the star, the passing shadow of a Dyson swarm under construction, the very kind of megastructure Freeman Dyson had imagined. Wright was scrupulous about this. He did not claim it was aliens. He framed it exactly as it should be framed, as the hypothesis of last resort, the explanation you turn to only after the natural ones have faltered, the one that carries the heaviest burden of proof and should be the hardest to accept. But he said it, in print, about a real star with a real name, and once that idea was attached to a genuinely unexplained object, the world responded as you would expect. Tabby's star became famous. And in a remarkable moment for science, the public itself helped fund the follow-up. A crowdfunding campaign raised the money for a network of telescopes to monitor the star continuously, so that the next time it began to dim, astronomers could catch it in the act and study the light in real time, in a way the archived Kepler data never allowed. The wait paid off. In 2017, fresh dips finally arrived while the monitoring network was watching, and for the first time, astronomers could study the dimming as it happened, across different colors of light at once. And that turned out to be the key that unlocked the deep dips. Because the star did not dim equally in all colors. It dimmed more in blue light than in red. And that single fact carries an enormous amount of information. A solid object, a planet, a moon, a megastructure made of solid panels would block all colors of light equally because a solid thing casts a solid, colorless shadow. But fine dust does not. Small particles of dust scatter and block blue light more effectively than red light, letting the red pass through more easily. The color signature of Tabby's dips pointed clearly to dust. Uneven, orbiting clouds of fine material, perhaps the shattered remains of a comet swarm, or the debris of a broken-up moon or planet, passing in front of the star in ragged, irregular clumps. For the dramatic short-term dips, the megastructure was not needed. Nature had an answer, and it was dust. And here is where the story becomes something quieter, and in a way sadder, than a simple solved mystery. Sit for a moment with what actually happened here. The deep dips got their natural explanation, and it was a good one, well supported, honest. The swarm of alien structures was not required to explain the flickering. But the strangest part of Tabby's star was never really the deep dips at all. Beneath them lay a second, subtler, more stubborn anomaly, and that one was not solved. Because when astronomers went back through the archives, through more than a century of old photographic plates on which this star had been unknowingly recorded across the decades of the 20th century, they found evidence that Tabby's star had been slowly, steadily dimming the whole time. Not in sudden dips, but in a long, gradual fade, growing quietly fainter across 100 years. And more than that, careful analysis suggested the star continued to fade even during the few years of the Kepler mission itself, dimming measurably over the course of the observations. A slow, secular, century-scale dimming is genuinely hard to produce, with the same passing clouds of dust that explain the short dips. Dust clouds pass, and the light returns. They do not, easily, make a star grow permanently and steadily dimmer over 100 years. And that long fade has never been cleanly explained. There is a particular feeling to this, and it is the real weight of Tabby's star. It is the feeling of a near miss. We reached, for a moment, for the largest possible answer, the idea that we might be watching an alien civilization building something around its sun. We built telescopes, we raised money from strangers who wanted to know. We caught the star dimming, and we found, for the loudest part of the mystery, a smaller and more ordinary answer: dust. And then, when the excitement had faded, we were left holding a quieter and more stubborn puzzle that is still open. The universe let us rehearse the biggest question we know how to ask. It let us feel, for a season, what it might be like to actually find something. And then it handed the rehearsal back to us unfinished, with the loud part answered and the deep, slow, century-long strangeness still sitting there, unresolved. That is not the thrill of discovery. It is the humility that comes after it, the recognition of how much we wanted the largest answer and how carefully we had to set it down. It is worth returning to why the early data made the megastructure idea so hard to dismiss out of hand, because the reasoning was sound, even though the answer turned out to be dust. When a star dims, the most common ordinary cause is a cloud of material passing in front of it, and warm material close to a star glows in the infrared as it absorbs the starlight and re-radiates it as heat. So one of the first things astronomers did with Tabby's star was look for that infrared glow, the telltale warmth of a dust cloud. And in the early data, they did not find the excess they expected. A dust cloud large enough to block a fifth of the star's light should have announced itself in the infrared, and it seemed not to. That absence is what made the natural explanations stumble at first, and it is what left the door open, briefly, for the idea that whatever was blocking the light might be something that did not glow like dust, something solid and cool, something possibly built. Later observations and a fuller understanding filled in the picture and pointed back toward dust after all, uneven and clumpy, and caught at the right moments. But the initial puzzle was genuine, and the megastructure question was raised responsibly as the answer of last resort when the obvious answer appeared, for a time, to fail. The leading natural picture for the deep dips, once the color evidence came in, involves the debris of a shattered body. Imagine a large comet or a small moon that was broken apart by the star's gravity or by a collision, its remains spread into an uneven, orbiting stream of dust and rubble. As that ragged stream passes in front of the star, it blocks light in irregular, unpredictable amounts, deep one week and shallow the next, never on a clean schedule, exactly matching the chaotic dips that Kepler recorded. And because it is fine dust, it dims blue light more than red, exactly as the real-time observations found. It is a satisfying explanation for the short dips, and it requires nothing exotic, only the ordinary violence of a planetary system rearranging itself. The megastructure was never needed for the dips once the dust picture came together. What the dust picture does not do, and this is the point that keeps the star on our list, is explain the slow, steady, century-long fade that seems to underlie the whole system. The story of how the star was found is itself part of why it matters, because it is a story about ordinary people noticing something extraordinary. The Kepler telescope produced far more data than any team of professional astronomers could examine by eye, and so a public project was created that let volunteers around the world scan the light curves that automated systems had flagged as unusual. These volunteers, amateurs giving their time out of curiosity, were the ones who kept returning to this one star, because its dips were so strange that they did not fit any of the categories the project had trained them to expect. They discussed it among themselves, flagged it as a genuine oddity, and brought it to the attention of the professional team. It is a genuinely moving fact that the most famous candidate for a megastructure in the history of astronomy was first singled out not by a supercomputer or a distinguished observatory, but by ordinary people patiently looking at graphs, noticing that one star refused to behave. The scientific debate over the long-term fade has been sharp, and it is worth being honest that it is not fully settled even as a matter of measurement. When one astronomer reported, from old photographic plates, that Tabby's star had dimmed by a noticeable amount across the 20th century, others challenged the finding, arguing that comparing century-old photographs is fraught with difficulty, that the plates and the way they were developed and measured changed over the decades in ways that could mimic a real fade. It became a genuine dispute about whether the long dimming was real at all. But further analysis, including careful study of the star's brightness during the precise, modern Kepler observations themselves, supported the idea that the star really was growing fainter over time, dimming measurably even across the few years of the mission. That modern evidence is much harder to dismiss than old photographs, and it is what keeps the secular fade alive as a genuine and stubborn anomaly rather than an artifact of aging film. It is also worth being clear about why the dust explanation, good as it is for the deep dips, sits uneasily with the long fade, because that tension is the whole reason the mystery survives. Passing clouds of dust explain a temporary dip beautifully. The dust moves in front of the star, blocks some light, moves on, and the brightness returns. That is a transient event, and it comes back. But a steady dimming that continues across years and possibly across a century is a different kind of thing entirely. To make a star grow permanently and progressively fainter, you need something more than a cloud passing by, something that keeps accumulating, or keeps growing, or keeps changing in one direction over a very long time. No one has produced a fully satisfying natural model that ties the ragged short dips and the slow century-long fade together into a single, clean story. They may be two separate phenomena afflicting the same star, or they may share a hidden cause we have not yet imagined. Either way, the loud part of the mystery got an answer, and the quiet part did not. So the honest status of Tabby's star is a divided one. Its dramatic short-term dips have a good natural explanation, uneven clouds of dust passing in front of the star. Its long, slow, century-scale fade does not, and remains genuinely difficult to account for. The megastructure explanation is not the leading answer for either, and it would be wrong to present it as though it were. But two real open questions remain. What produces the apparent secular dimming across 100 years, which passing dust does not comfortably explain? And whether the deep dips and the long fade share a single hidden cause, or are two entirely separate phenomena that happen to afflict the same unlucky star. And beyond the specific puzzle, Tabby's star did something for the whole field that outlasts whatever its final answer turns out to be. More than any other object, this one ordinary-looking star turned the search for someone else's machinery from a fringe idea whispered about at the edges into a mainstream scientific question that serious astronomers were willing to investigate, to fund, and to name in print. It made the search respectable, It showed that when a genuinely unexplained object appears, it is legitimate to at least ask the largest question, as long as you are willing to test it honestly and follow the evidence wherever it leads, even when it leads to dust. That is what Tabby's star leaves us with. One unremarkable star in the constellation of the Swan let the entire species ask, out loud and seriously, whether we might be looking at something built. And even after the easy part of the mystery was answered, it kept just enough of itself unexplained to keep the question alive. A star can dim for reasons we half understand. But a signal, a single deliberate-looking pulse of radio from the depths of the sky, can arrive for reasons we do not understand at all. And the next entry on our list is the most famous such signal ever recorded, 72 seconds of noise that has haunted radio astronomy for nearly 50 years. Number 3. 72 seconds. On the 15th of August 1977, a radio telescope in Ohio recorded 72 seconds of noise that has never been explained and never been repeated, and that remains, nearly 50 years later, the most famous signal in the history of the search for extraterrestrial intelligence. The telescope was called Big Ear, a huge, flat, ground-based instrument run by Ohio State University, built to scan the sky for radio waves. It did not move quickly. It let the rotation of the Earth carry the sky past its stationary view, listening patiently to whatever drifted through its beam. And on that August night, something drifted through that it had been built, in part, to find. The signal was not seen live. It was recorded automatically, printed out as a grid of letters and numbers representing signal strength, and it was several days later that an astronomer named Jerry Eman sat down to review the printout. Most of the page was ordinary background noise, represented by low numbers and blanks. But in one column, Eamon found a sequence that leapt off the page, a burst of signal far stronger than anything around it, climbing steeply above the background and then falling away. The intensity was written in a code of digits and letters, and the peak of it read 6EQUJ5. Eamon was so struck by it that he circled the sequence in red pen and wrote a single word in the margin beside it. He wrote, "Wow." And that word became the name of the signal, and the name of a mystery that has outlived the telescope that heard it. What made the wow signal so compelling was that it had, all at once, several of the exact properties you would expect from a deliberate transmission. Consider them one at a time, because the accumulation is the whole point. First, it was narrowband. That means the signal was concentrated in an extremely tight sliver of frequency, rather than spread out across a wide range. This matters enormously, because the natural universe is loud and messy. Stars, galaxies, clouds of gas, they emit radio noise smeared across broad ranges of frequency. Producing a signal concentrated in one narrow channel is something that engineered transmitters do easily, and that only a very few rare natural processes can manage. A narrowband signal is, in a sense, the fingerprint of a tuned device. Second, the frequency itself was meaningful. The wow signal came in close to 1420 MHz, which is the natural frequency of neutral hydrogen, the most common substance in the universe. Decades earlier, theorists searching for a logical channel on which civilizations might choose to signal had argued for exactly this frequency, reasoning that hydrogen is everywhere, that every radio astronomer in the galaxy would know its frequency and be watching near it, and that it would therefore make a natural universal meeting place, a cosmic waterhole where anyone trying to be found might broadcast. The wow signal arrived right there, in the one part of the radio spectrum that a signaling civilization was most expected to choose. Third, it was strong, roughly 30 times louder than the ordinary background hum of the sky. And fourth, its shape over time was exactly right. The signal rose and fell over about 72 seconds, and that specific duration is precisely what you would expect from a fixed point in the sky drifting through Big Ear's stationary beam as the Earth turned. A local source, something on the ground or in orbit, would not usually produce that clean, expected rise and fall matched to the telescope's fixed field of view. But a genuine point of radio emission, sitting still in the distant sky while the Earth rotated the telescope past it, would trace out exactly that 72-second curve. Everything about the signal said that it was out there, far away, and not in the building. The telescope that caught it deserves a moment of description, because its design is why the signal has the shape it does. Big Ear was not a dish that could swivel and track a target across the sky. It was a huge, fixed, flat instrument that lay open to the heavens and simply let the Earth's rotation carry the sky slowly across its field of view. This is called a drift scan, and it means that any genuine point of radio emission out in space would take a fixed, predictable amount of time to drift through the beam, rising in strength as it entered, peaking at the center, and fading as it left. For Big Ear's beam, that transit took a little over a minute. And that is precisely the profile the WOW signal traced, a rise and a fall over about 72 seconds, exactly matching what a fixed celestial source should do. A signal from a passing satellite or a source on the ground would generally not produce that clean, expected shape tied to the telescope's fixed geometry. The very design of Big Ear, its stillness, its reliance on the turning Earth, is what makes the signal's behavior so consistent with a real, distant, celestial origin, and so hard to blame on something local. It is worth remembering, too, that this was the fruit of patient, unglamorous work by people who spent years listening to noise. The search that Big Ear was conducting had gone on for a long time, night after night, recording the hiss of the sky onto printouts that a human being then had to review by hand, page after page, looking for anything that stood out. Jerry Amon was doing exactly that ordinary, tedious task when he found the extraordinary thing, and his instinctive scrawl of a single word in the margin, "Wow," has outlived the telescope, the printout, and nearly everyone involved. There is something fitting in that. The most famous moment in the history of the search for other minds was not a dramatic contact, but a quiet act of attention. A man noticing a column of numbers that climbed too high, days after the sky had already moved on. And then there is the fact that has tormented the field for nearly 50 years. It never came back. Big Ear returned to that same patch of sky, in the constellation Sagittarius, again and again. Other telescopes, larger and more sensitive, searched the same spot in the years and decades that followed. And there was nothing. Never again a whisper. A genuine repeat of the WOW signal would have transformed it in an instant from a tantalizing curiosity into the single most important detection ever made by human beings, a confirmed, repeatable signal from the stars. But the repeat never came. And its silence is exactly what makes it maddening. For 72 seconds, a telescope recorded something that looked in every measurable way like the thing that the entire search had been built to find. And then it fell silent forever. Big Ear itself did not survive. The telescope was demolished in 1998, and the site where it once listened to the sky is now a golf course. Let me put you in the quiet of that discovery, because the human reality of it is stranger than the alien fantasy. Imagine the scene. It is days after the signal came and went. A man sits at a desk with a thick stack of computer paper, the continuous printout of everything the telescope recorded, page after page of characters representing the strength of the sky. He is reviewing it by hand, line by line, in the ordinary way, expecting nothing. And then his eye catches a column where the numbers climb without warning, far past anything the machine has logged, a steep spike of signal rising out of the noise and falling back. He knows immediately that it is unusual. He reaches for a red pen. But here is the strange, deferred heart of it. The telescope that heard the signal was already looking somewhere else by the time he read the page. The signal was only 72 seconds long, and it had ended completely before a single human being knew it had ever happened. The most famous candidate signal in the history of the species was not witnessed. It was discovered, later, in ink, on paper, in silence. No one heard it arrive. No one was listening in the moment. It came and it went, and only afterward, in a quiet room with a stack of paper, did anyone realize what might have passed. Part of what has kept the wow signal in the conversation for so long is that it sits at an uncomfortable middle distance between the ordinary and the extraordinary. If it had been obviously artificial, obviously a repeating, structured, unmistakable message, it would have changed the world. If it had been obviously natural, obviously a satellite or a known source, it would have been forgotten within a week. Instead, it landed exactly in between, a single event with several of the properties of a deliberate signal and none of the confirmation, too clean to easily dismiss and too brief and solitary to accept. That middle distance is precisely where a mystery becomes durable, because it can be neither proven nor disproven, only turned over and over. Nearly 50 years of turning it over, by serious people with better and better instruments, has neither confirmed it nor explained it away, and that endurance is itself a kind of proof of how genuinely strange those 72 seconds were. Over the years, natural explanations have been proposed and mostly set aside. One suggestion held that a passing comet, surrounded by a cloud of hydrogen, might have produced the signal, but that idea was examined and found unconvincing, unable to account for the signal's properties. And then, in the year 2024, a team associated with a project revisiting the WOW signal offered the most complete natural explanation yet advanced. Re-examining the event in detail, they proposed that the signal could have been produced by a sudden brightening of hydrogen in an interstellar cloud, triggered by a burst of intense radiation from a passing source, such as a magnetar, a kind of extreme, magnetized dead star known to flare violently. Under the right conditions, that flash of radiation could cause the hydrogen to emit in a narrow, brief, intense burst, a rare natural process, a little like a laser, but working in radio, a maser flare. If they are correct, the WOW signal would be the first ever recorded flare of its kind in the hydrogen line, a natural event rather than a message. It is a genuinely strong hypothesis, worked out with care. But it is not confirmed. The proposed source has never been caught repeating the trick, and the signal remains, officially and honestly, unexplained. Two questions still hang over it. Whether that 2024 explanation, the magnetar-triggered flare of hydrogen, is actually correct, which would require catching the mechanism in the act somewhere else. And why, after nearly 50 years of listening with ever better instruments, that exact spot in the sky has never produced anything again. Before we leave it, it is worth noting one more case, quieter than the WOW signal but instructive. In 2019, another radio telescope, listening to our very nearest neighboring star, Proxima Centauri, picked up a signal that also looked, for a while, textbook perfect, a narrow-band tone that behaved suspiciously like a transmission. It was studied intensely for over a year, and in the end, it was traced not to the stars but to human electronics here on Earth, a piece of our own technology producing interference that happened to mimic the real thing. That case was solved, and it was solved as a caution. It is a reminder of how easily our own machines can wear the mask of a signal, and of why the field insists on such patience. The WOW signal has never been solved that way. It has never been traced to anything at all. It is worth understanding why the hydrogen frequency carried such meaning, because it is one of the most elegant ideas in the whole history of the search. Back in 1959, two physicists reasoned about the problem of how two civilizations that had never met and shared no language might nevertheless choose the same radio channel to look for each other. They realized that the universe itself provides a natural landmark. Neutral hydrogen, the most abundant substance in the cosmos, glows faintly at one specific frequency, near 1,420 megahertz, and every radio astronomer anywhere in the galaxy would know that frequency and would build instruments to observe it, because it is how you map the gas of galaxies. So that frequency becomes a kind of universal meeting place, a cosmic watering hole where any species trying to be found might reasonably broadcast, knowing that anyone else who was listening would be listening there. The WOW signal arrived right at that watering hole. Whatever its true source, it appeared at exactly the frequency that decades of careful reasoning had marked as the most likely channel for a deliberate signal. That is part of what made it so hard to shrug off. The decoding of that famous string, 6EQUJ5, is worth explaining because it sounds like a message and is not. Big Ear recorded the strength of the signal in each moment using a compressed code where low numbers marked faint signals and, once the strength climbed past 9, letters took over, with each successive letter marking a higher intensity. So the sequence 6EQUJ5 is not a word or a code from anyone. It is simply the rising and falling loudness of the signal written in that shorthand, climbing from a 6 up through the letters to U, the loudest moment, and then falling back down. Read in order, it traces the exact shape of a source rising to a peak and fading over about 72 seconds, precisely the profile a fixed point in the sky would make as the Earth's rotation swept it through the telescope's stationary beam. The famous string is not the message. It is the shape of the silence being broken and then resuming. In the years after the discovery, the search for a repeat became something of a quiet obsession for parts of the field, and the failure of that search is its own kind of evidence, though of what, no one can say. Astronomers pointed larger and more sensitive instruments at the same patch of sky, listened for hours, listened for days, returned across the decades, and heard nothing. One amateur astronomer, working long after the fact, even tried to narrow down which star in that region the signal might have come from, identifying a sun-like star in roughly the right direction as a candidate origin, though nothing has ever confirmed a connection. The point of all this listening is that a genuine, repeating signal would have changed everything, would have lifted the WOW signal out of the category of tantalizing curiosity and into the category of the most important discovery ever made. Its stubborn refusal to return is what keeps it exactly where it has always been, a single unrepeatable event, too good to explain away and too silent to confirm. That is what the WOW signal leaves us with. For 72 seconds, a telescope recorded exactly what we had spent decades listening for, and the fact that we can neither confirm it nor make it return is the closest thing that the search for other minds has to a ghost story told in data. That whisper, whatever it was, came from within our own galaxy, from a fixed point in the sky, and never spoke again. But the next strangeness on our list did not come from within our galaxy at all. It came from another star entirely, an object that fell through our solar system carrying the chemistry of a different sun. And unlike the WOW signal, this time we got to watch. Number 2, the second visitor. In July of the year 2025, a survey telescope belonging to a network called Atlas picked up a faint point of light moving through the inner solar system, and within days it became clear that this object was not from here. Its path could not be closed into an orbit around the Sun. The trajectory was hyperbolic, an open curve rather than a loop, and its speed was too high for the Sun's gravity to ever hold it. It had come from somewhere else, from the space between the stars, and it was only passing through. It was catalogued as 3I Atlas. The 3 marks it as the third confirmed interstellar object ever detected inside our solar system, following the first, called Oumuamua, in 2017, and the second, a comet called Borisov, in 2019. And by many measures, 3I Atlas became the most closely studied visitor from another star that we have ever caught. The reason we could study it so well is that, unlike the first visitor, 3I Atlas behaved partly like a comet. It had a coma, a diffuse cloud of gas and dust surrounding it, produced as the sun warmed its surface and material boiled away. That gave telescopes something to analyze, a glowing envelope whose composition could be measured. And because it was found relatively early and moved through the inner solar system over a stretch of months, astronomers had time to watch it approach the sun, round it at its closest point in late October of 2025, and begin its long departure back into the dark. That extended window of study turned up a whole series of genuine oddities, each of which is worth looking at, because it is the accumulation that made this object so compelling. Before we walk through its oddities, it is worth pausing on why an interstellar object is such a precious thing to catch at all. Every comet and asteroid in our own solar system formed here, out of the same cloud of gas and dust that made the sun and the planets more than 4.5 billion years ago. They are all, in a sense, siblings, born of one nursery, carrying variations on one shared chemistry. But an interstellar object formed somewhere else entirely, around another star, out of a different cloud, under conditions we have never directly sampled and can only guess at. When one falls through our neighborhood, it is a physical piece of another planetary system, delivered to us for free, a fragment of a place we could never reach with any spacecraft we know how to build. To hold such a thing in the view of our telescopes, even briefly, is to read a line from the biography of another star. That is why astronomers drop everything when one appears, and why 3I Atlas, comet-like enough to study in real detail, was treated as the opportunity of a decade. The first oddity was in its early chemistry. As 3I Atlas approached, while it was still far from the Sun, the James Webb Space Telescope examined the gas around it and found that the coma was dominated not by water vapor, but by carbon dioxide. That is unusual. Most comets, as they warm, are driven primarily by water ice turning to vapor, the most abundant ice in a typical comet. To find a coma dominated by carbon dioxide, seen while the object was still far out and cold, before significant water sublimation had begun, hinted at a body with a different balance of ices than the comets born in our own solar system, a frozen sample of the chemistry of another star. Early spectra also suggested the object was strongly depleted in the carbon chain molecules that ordinary comets carry, though later observations softened that picture as the object drew closer and revealed more of itself. But the most striking anomaly was in the metals. When astronomers measured the gas around 3I Atlas, they found an unusually high ratio of nickel to iron, well outside the range measured across thousands of ordinary comets. Nickel and iron are chemically similar and usually appear together in comet gas in fairly predictable proportions. This object had far more nickel relative to iron than expected, and in one striking framing, the proportions resembled those found in industrially produced nickel alloys, with a ratio of nickel to cyanide orders of magnitude larger than anything seen in the thousands of known comets. That is the kind of detail that, stated starkly, sounds almost manufactured, and it drew intense attention and no small amount of speculation. The carbon dioxide-dominated coma is worth pausing on, because it is a genuine window into the frozen chemistry of another star system. Most comets born in our own solar system are driven primarily by water ice, and their comas fill with water vapor as they warm. To find a coma dominated instead by carbon dioxide, and to find it while the object was still far from the sun and cold, before water ice would readily turn to vapor, suggests a body that formed in a different place or under different conditions than the comets of our own family. It hints at a home system whose planet-forming disk carried a different balance of ices, richer in frozen carbon dioxide relative to water, a subtle but real fingerprint of a nursery around another star. We cannot travel to that nursery. We will never see the disk it formed in. But for a few months, its chemistry drifted through our sky in the form of a single frozen wanderer, and we read what we could of it before it left. There were oddities in its motion and geometry as well. The object's incoming path was aligned surprisingly closely with the flat plane in which the planets orbit, a coincidence with fairly low odds, perhaps a fraction of a percent by some estimates, that a randomly arriving interstellar object would happen to come in so nearly along the planetary plane. Careful processing of images from the Hubble Space Telescope, taken across late 2025 and into early 2026, revealed a symmetric system of small jets around the object, structured and regular in appearance. And analyses of its trajectory reported a non-gravitational push, an acceleration not fully accounted for by the Sun's gravity, with in some readings a component directed sideways rather than simply straight outward from the Sun. Each of these features, taken entirely on its own, has a plausible natural explanation. Jets from an irregular rotating comet can look structured. Non-gravitational forces are routine for outgassing bodies. Alignments happen by chance. But taken all together, the pile of oddities is why 3I Atlas drew more scrutiny and more open speculation about whether it might be something other than natural than any comet in living memory. And this is where the honest resolution matters, because it is a good example of how observation settles what speculation cannot. The mainstream reading held by most of the astronomers who studied it is that 3I Atlas is a genuinely unusual but entirely natural comet, a frozen relic from the planet-forming disk of another star, carrying a chemistry shaped by conditions we have never sampled directly. And that reading was strengthened, crucially, by watching the object change. Its most exotic feature softened under observation. After the object rounded the Sun, its nickel-to-iron ratio fell back toward ordinary values, and its overall character came to resemble that of a well-known comet from our own solar system, a body called 9P Tempel 1. That is the behavior of unusual but natural chemistry responding to the Sun's heat, not the behavior of a machine. The strangeness was real, and it was largely the strangeness of a comet from an unfamiliar place, revealing itself as it warmed. Still, the object is now fading. It is on its way back out of the solar system, dimming as it recedes, carrying its remaining secrets with it, and several of its anomalies were never fully explained before it left. It is the freshest entry on this entire list, precisely because the ink is still wet, because it happened so recently that the analysis is ongoing even now. Twice in less than a decade, something from another star has fallen through our neighborhood, and each time it has let us read a fragment of a system we will never visit. 3I Atlas gave us the fullest reading yet, months of study, spectra, images, a whole campaign trained on a single wanderer. And even so, it left with at least a few questions unanswered. What produced its extreme early nickel signature, and why it normalized after the Sun's heat worked on it? The origin of that reported sideways component in its motion, and what its carbon dioxide-rich coma implies about the frozen chemistry of the distant system where it was born. The observations of 3I Atlas were among the most thorough ever assembled for a comet, and the sheer range of instruments trained on it is part of why its oddities are so well documented. Ground-based telescopes tracked its brightness and its path. The James Webb Space Telescope read its coma chemistry in the infrared, finding the carbon dioxide. Other space telescopes reobserved it after perihelion and reported continued activity, fresh dust, and new gas species appearing as it warmed. The Hubble Space Telescope imaged it repeatedly, And it was the careful processing of dozens of those Hubble images across several months that teased out the symmetric structure of small jets around the object. This was not a passing look. It was a sustained campaign, and it produced a rich, detailed record precisely because the object cooperated by being active and by staying observable for months. The very completeness of that record is what let astronomers watch its strangest feature, the extreme nickel signature, rise and then subside, a change over time that a single snapshot could never have revealed. The nickel anomaly deserves one more careful look, because it is the detail most likely to be remembered and most easily misunderstood. When astronomers measure the gas around a comet, they routinely see traces of nickel and iron vapor, and across the thousands of comets studied, those two metals appear together in a fairly consistent range of proportions. 3I Atlas, in its early observations, showed a ratio of nickel to iron well above that range, more nickel relative to iron than essentially any comet on record. Stated bluntly, and it was stated bluntly, the proportions resembled those found in certain industrially produced metal alloys, which is the kind of comparison that inevitably sparks speculation. But unusual metal ratios have been seen in a few solar system comets too, produced by exotic but entirely natural chemistry, involving how these metals are released from the ice at low temperatures. And the decisive point is what happened next. As 3I Atlas was heated by its passage around the Sun, the ratio shifted, falling back toward ordinary comet values, until the object's overall chemistry came to resemble a familiar comet from our own solar system. That evolution, from bizarre toward ordinary as the Sun did its work, is the signature of natural chemistry responding to heat, not of a fixed, manufactured composition. It helps to place 3I Atlas in the very short history of interstellar visitors, because there are only 3, and each has taught us something different. The first, in 2017, was the strange, tumbling, gasless object we will come to at number 1, gone almost before we understood it. The second, in 2019, was a comet that behaved almost boringly, like the comets of our own system, a reassuring sign that most wanderers between the stars are ordinary. And now the third, in 2025, arrived as something in between, comet-like enough to study in detail, strange enough in its chemistry and behavior to reward that study with a whole catalogue of oddities. 3 objects, in less than a decade, after all of human history with none. That in itself is a discovery. It tells us that these visitors are not once-in-a-civilization rarities, but a genuine, if thin, traffic, and that as our sky surveys grow sharper, we will catch more of them, more often, and learn to read them faster. The intense study of 3I Atlas also became a case study in how speculation and science interact in public, and that is worth being honest about. Because the object showed so many oddities at once, the carbon dioxide coma, the extreme nickel ratio, the near alignment with the planetary plane, the structured jets, the reported sideways push, some voices raised the possibility that it might not be natural at all, that it might be something sent or built. Those suggestions drew enormous attention, far more than the quieter mainstream analysis. But the mainstream analysis is what actually resolved the picture, patiently, feature by feature, as more data came in. The alignment turned out to be an unlikely but acceptable coincidence. The jets fit a rotating, irregular, outgassing body. And most tellingly, the extreme nickel signature, the single most manufactured-sounding detail, faded after the object rounded the Sun, its chemistry settling toward that of an ordinary comet from our own system. The strangeness was real, and it was, as far as the evidence can tell, the strangeness of nature, revealed by watching rather than by guessing. And that is finally the deepest value of 3I Atlas, beyond any single anomaly. It was a genuine sample of another star system, delivered to our doorstep, free of charge, and we were ready enough to study it closely. Every comet in our own solar system formed from the same cloud that made the Sun and the planets, so they all share, broadly, a common origin and chemistry. But 3I Atlas formed somewhere else entirely, around a different star, out of a different cloud, under conditions we have never sampled. Its carbon dioxide-rich ice, its unusual metals, its whole composition is a message about a place we will never visit, written in frozen chemistry rather than radio waves. We got to read a few lines of that message before the object faded back into the dark. And knowing that another one will come, and then another, changes the interstellar dark from a barrier into something more like a shore, where now and then the tide leaves something we can pick up and examine. That is what 3I Atlas leaves us with. A messenger from another star, studied harder than any before it, mostly explained and still holding back a little. It behaved oddly, but in the end, mostly like a comet, and it let us watch the whole way through. But there was an earlier visitor, the first one, and that one did not behave like a comet at all. It behaved like nothing we have ever seen, before or since. It showed no coma, no tail, no gas, and yet it sped up as it left. And it did not let us watch. It was gone almost before we understood what we were looking at. That first visitor is number 1 on our list. Number 1, the object that sped up. On the 19th of October 2017, a telescope in Hawaii called Pan-STARRS, built to scan the sky for moving objects, detected a faint point of light traveling through the solar system far too fast for the Sun to hold. Astronomers traced its path and found the same open hyperbolic curve that would later mark 3I Atlas, but this was the first time humanity had ever seen it. This was the first confirmed interstellar object ever detected inside our solar system, the first fragment of another star system we had ever caught passing through our own. It had come from the depths of interstellar space, fallen briefly toward our Sun, and was already on its way back out. Astronomers gave it a Hawaiian name, Oumuamua, meaning a scout or a messenger, reaching out from the distant past, arriving first. And it is number 1 on this list because, of everything that human beings have ever discovered, it is the single object whose behavior we have least been able to explain. And it is already gone. From the very beginning, Oumuamua broke the pattern of everything we knew. As astronomers tracked it in the brief window before it faded from view, they watched its brightness swing wildly and regularly, rising and falling by a large factor as the object tumbled end over end through space. The only way to produce a brightness that varied so dramatically was for the object to have an extreme shape, far more elongated than any asteroid or comet ever recorded. The measurements suggested something several times longer than it was wide, perhaps like a long, stretched cigar, or, in another interpretation of the same data, like a flat, wide, thin sheet, a kind of cosmic pancake. Neither shape resembled anything in the catalogue of ordinary solar system bodies. That alone would have made Oumuamua a curiosity worth remembering. But the truly unexplained part, the reason it sits at number 1, came as it left. As astronomers tracked Oumuamua receding from the Sun, they found in 2018 that the object was accelerating. It was speeding up as it moved away, gaining velocity by an amount that the Sun's gravity alone could not account for. Something was giving it an extra push, and gravity was not the source. Now, for a comet, that would be completely routine, and it is worth understanding why, because the absence of the explanation is the whole mystery. When a comet approaches the Sun, sunlight heats its surface, and the ices there turn to gas and stream away. That escaping gas acts like a gentle, natural rocket, giving the comet a small push in the opposite direction. Astronomers see this all the time. It is called non-gravitational acceleration, and for a comet, it is expected, ordinary, even boring. So when Oumuamua showed the same kind of acceleration, the natural first thought was that it must be a comet, quietly outgassing, pushed along by its own escaping vapor. Except that Oumuamua showed no signs of outgassing at all. It had no visible coma, no glowing envelope of gas around it. It had no tail. It showed no jets. And when astronomers examined its light with spectroscopy, searching for the telltale fingerprints of escaping gas, they found nothing. Multiple observatories looked hard, precisely because the acceleration demanded a cause, and the search for that cause came up empty. There was no visible vapor, no detectable gas, no observable mechanism to produce the push. And yet the object was measurably speeding up, gaining velocity through the empty dark, with no source that anyone could see. That is the fact about Oumuamua that has never been cleanly resolved. It accelerated, and we could not find the reason. Sit with what this finale actually is, because it is the landing of everything we have walked through tonight, and the feeling it leaves is not fear. It is a very old kind of wonder, mixed with a very real kind of loss. Oumuamua is gone. It did not linger. It is receding into interstellar space right now, already far beyond any reach we have, any probe we could send, any telescope that could still resolve it. It is carrying its answer with it into the dark, and it is not coming back. We got a few weeks. A handful of nights of measurements on a faint, fading smudge of light, caught almost by accident, studied in a hurry, and then it was past us and gone. The single most anomalous object that human beings have ever encountered passed through our solar system exactly once, behaved in a way we still cannot fully explain, and left before we could be sure what it was. Whatever it was, natural or something stranger, we will not get it back. The only thing we can do now is get better at watching, so that the next one does not leave us holding only questions. The explanations offered for the acceleration are many, and most of them are natural, and none of them has become settled fact. Perhaps Oumuamua was outgassing something we simply could not detect. One idea proposed that it was releasing hydrogen gas, invisible to our instruments, from ice that had built up over its long journey between the stars. Another suggested it was venting nitrogen, that it was a chip broken off the frozen nitrogen surface of a distant world like Pluto, a shard of an alien ice cap pushed along by nitrogen quietly boiling away. Another proposed that Oumuamua was extraordinarily fluffy and porous, so light and airy that the faint pressure of sunlight itself could push it measurably, like a leaf caught in a sunbeam, an accidental sail. Each of these ideas is plausible. Each of them also has problems, features it explains poorly or requires us to assume without evidence. None has risen to become a consensus that the whole field accepts. And there is one more idea, the one that has to be named on a list like this, raised by the Harvard astronomer Avi Loeb, and it is a minority view, sharply contested and entirely unproven. Loeb pointed out that an object which is pushed by sunlight, which shows no outgassing at all, and which may be shaped like a thin, flat sheet, is precisely what an artificial light sail would look like, a piece of engineered technology, perhaps long dead and derelict, drifting between the stars from a civilization we cannot imagine. He argued that when the ordinary explanations struggle, the extraordinary one at least deserves to be considered and tested rather than dismissed. Most of his colleagues disagree, and they have good reasons, and it must be stated plainly that there is no proof, and that the light sail idea is very far from the accepted explanation. But it survives, on this list and in the literature, for exactly the same reason every entry tonight survives. Because the ordinary explanations have not fully closed the case. It is worth being fair about why most scientists resist the artificial interpretation, because their resistance is not closed-mindedness but discipline. The history of science is full of moments when an unexplained phenomenon was, too quickly, attributed to the most exciting possible cause, only for a mundane explanation to emerge later. Unusual pulses in the sky turned out to be spinning dead stars, not beacons. Strange signals turned out to be interference. The default assumption, hard-won through centuries of being wrong in the other direction, is that a natural explanation exists even when we have not yet found it, and that the burden of proof for anything else is enormous. So when most astronomers look at Oumuamua, they conclude that it was almost certainly a natural object of some unusual kind, and that our failure to pin down which kind reflects the poverty of our data gathered in a rush over a few weeks, rather than the presence of something built. That is a reasonable position, and it is probably correct. But probably correct is not the same as settled, and the honest truth is that no single natural model has accounted for everything the object did. The follow-up is the honest measure of where we stand. When the second interstellar visitor, the comet Borisov, arrived 2 years later, it looked and behaved like an ordinary comet, a natural control case, reassuring us that most visitors from other stars are exactly what we would expect, unremarkable balls of ice and dust. And 3I Atlas, higher on this very list, gave us a second, far closer, far longer look, months of study on a wanderer we could actually watch. But neither of them settled Oumuamua, because Oumuamua is the one that got away. It is the only one that accelerated with no cause we could see, and we saw it for only a few weeks, and it is never coming back. Its silence is different from the WOW signal's silence. The WOW signal at least stayed at a fixed point in the sky we could return to. Oumuamua is a moving target that has already left the field of play forever. We are trying to be ready for the next one. New observatories are being built and brought online specifically to catch the next interstellar wanderer earlier, to detect it while it is still approaching rather than already departing, to study it for months instead of weeks. There are even proposals, still unfunded, for missions that could chase such an object down and fly alongside it. The hope is that if another object ever behaves the way Oumuamua did, if another visitor accelerates for no visible reason, we will not be caught flat-footed and watching it recede. We will be prepared to follow, to study, to finally answer the question that Oumuamua left open. Until then, the strangest thing we have ever found remains exactly that, an open question receding into the dark, gaining speed for reasons we cannot name, carrying whatever it was beyond our reach. The way its shape was determined is itself a lovely piece of detective work, worth understanding because it shows how much can be read from so little. No telescope could actually see Oumuamua as anything but a point of light. It was far too small and too distant to show a disk or a form. What astronomers had was its brightness, measured over time, and that brightness swung up and down by a factor of roughly 10 as the object tumbled. An object that changes its brightness that dramatically as it rotates must be presenting very different amounts of surface to us at different moments, which means it must be extremely elongated, far more so than any asteroid or comet in our own solar system, which tend to be lumpy but roughly rounded. From the pattern of that flickering, they reconstructed a body several times longer than it was wide, and the debate over whether it was more like a long rod or a flat disk came down to competing readings of that same rising and falling light. An entire argument about the shape of a visitor from another star, conducted on the evidence of a point of light growing brighter and dimmer as it spun. There was another telling result, this one from the search for heat. After the object was discovered, the Spitzer Space Telescope, which sees in the infrared, was turned toward it to try to detect the warmth it should radiate. Spitzer looked, and it saw nothing at all, no infrared glow above its sensitivity. That non-detection was informative in its own quiet way. It placed a limit on how large the object could be, because a larger body would have radiated more heat than Spitzer's silence allowed, and it also suggested the surface might be more reflective than a typical dark comet. Even the failure to detect something became a clue, narrowing the picture of what Oumuamua could and could not be. This is how the study of it went: scraps of evidence assembled in a hurry, each one carving away a few of the possibilities, none of them ever quite reaching the center of the mystery. The deeper lesson astronomers took from Oumuamua is about readiness, and it is reshaping how we watch the sky. The reason we learned so little was that we caught the object late, on its way out, with instruments that were not designed to respond quickly to a fast-moving interloper. That is changing. A powerful new survey observatory, built to scan the entire visible sky over and over, night after night, is designed precisely to catch fleeting moving objects early, while there is still time to study them. When it and others like it are fully at work, astronomers expect to find interstellar visitors more often, and to spot them sooner, on the way in rather than on the way out. The hope is simple and pointed. If another object ever behaves the way Oumuamua did, if another one accelerates for no reason we can see, we want to have found it early enough to study it properly, and perhaps even to send something after it, rather than watching it dwindle into the dark with its secret intact. It is worth dwelling on how little time we actually had, because the brevity is part of what makes Oumuamua unique among everything on this list. By the time it was discovered on its way out, it was already faint and receding, and it was visible to our telescopes for only a matter of weeks before it dimmed beyond reach. In that narrow window, astronomers scrambled to gather everything they could, pointing every available instrument at a smudge of light that was disappearing, even as they watched. There was no second chance, no returning to the same patch of sky, no waiting for it to come around again, because it never will. Everything we will ever know about Oumuamua was gathered in those few crowded weeks in the autumn of 2017. Compare that to 3I Atlas, studied for months, watched through its whole passage around the sun. Oumuamua gave us almost nothing by comparison, and left us with the largest question. It is the thinness of the data, as much as the strangeness of the object, that has kept the argument alive. Some of the natural explanations deserve a closer look, because they show how hard scientists worked to keep this object inside the ordinary, and how each attempt strained against some stubborn fact. The idea that Oumuamua was a shard of frozen nitrogen, chipped off the icy surface of a distant Pluto-like world, was clever, and nitrogen ice venting invisibly could in principle provide the push. But it required that such fragments be common enough to plausibly reach us, and the numbers were difficult. The idea that it was outgassing hydrogen from ice built up over eons in interstellar space was likewise ingenious, and likewise had to assume properties we could not confirm. The idea that it was an extraordinarily porous, fluffy fragment, light enough to be shoved by sunlight alone, could explain the acceleration without any gas at all, but demanded a structure flimsier than almost anything in nature. Each explanation solved the central problem, the causeless push, and each paid for it by requiring something unusual to be true. None was impossible. None was proven. And the fact that the ordinary answers all required something extraordinary is precisely why the object still refuses to settle. There is a particular kind of scientific grief in this, the grief of the sample you cannot get back. In most of science, if an experiment is unclear, you run it again. If an observation is ambiguous, you make another. But Oumuamua was a single event, unrepeatable in principle, a thing that passed through once in the whole history of our species and is now gone forever into interstellar space, carrying whatever it was beyond any hope of recovery. We cannot point a better telescope at it next year. We cannot send a probe to catch it, though people have sketched the trajectories such a chase would need and found them just beyond our reach. Whatever answer Oumuamua held, it is leaving with it, at tens of kilometers per second, into a dark it will not emerge from for millions of years. The most anomalous object we have ever found is also the one we can never re-examine, and those two facts together are what make it the strangest discovery on this entire list. The honest weight of the whole list gathers here, at number 1. We began with chemistry that could cradle life, and ended with an object we cannot explain, and along the way, not one of these 10 discoveries closed the question, and not one of them closed it in either direction. The ordinary explanations kept almost, but never quite, closing the case. One visitor let us watch, and one got away. And every single entry, from the membranes falling into Titan's seas to the object accelerating into the dark, was, and remains, a result we cannot yet explain. That word, yet, is the entire point. It does not mean we are ignorant. It means we are early and still watching. So that is the list. 10 real discoveries, counted down from a moon where the rain is not water, to an object that fell through our solar system once and sped away without explanation. We passed the chemistry that could build a cell without water on Titan, the ocean that may stare out from the face of LHS 1140b, the contested breath of life in the air of K218b, and the leopard spots sealed in a tube on the surface of Mars. We stood before 7 stars that glowed wrong in the infrared, a single star flooded with elements that should not be there, and another that appears to have been quietly going out across 100 years of photographs. We listened to 72 seconds of noise that never returned, watched a visitor from another star reveal itself as it warmed, and ended with the one object we have never been able to account for at all. Not one of these 10 is proof that we are not alone. That is worth saying one final time, plainly, because it is the most honest thing about the whole night. Every one of them has a natural explanation waiting to be confirmed, or a leading interpretation that may yet win out, or a quiet answer that could arrive with the next observation and dissolve the mystery entirely. That is not a disappointment. That is what it looks like to ask the largest question carefully, with instruments instead of hopes, and to refuse to answer it before the evidence is in. But notice what all 10 have in common, because it is the real reason to have listened. In every case, the ordinary explanation has not fully closed the case. The universe keeps handing us results that sit just past the edge of what we can currently explain, and it does so not once but again and again, in the chemistry of frozen moons, and the light of distant stars, and the paths of objects that visit and leave. We are not living at the end of this search. We are living near the beginning of it, in the first generation with the instruments to even ask these questions properly. And the honest answer to whether we are alone is not yes, and it is not no. It is the quietest and most patient word we have. Not yet. We do not know yet. We are still watching. There is a particular comfort in that word, not yet, if you let yourself feel it. It means the story is not over. It means that we happen to be alive in the narrow window of history when the tools to ask this question finally exist, when a telescope can read the air of a world 100 light-years away, when a rover can drill an ancient lakebed on Mars, when a survey can sift 5 million stars for the heat of someone else's machinery. For every generation before ours, the question of whether we are alone was pure wondering, with no way to check. For every generation after ours, some of these mysteries will have been closed, one way or the other. We are living in the middle of the looking, in the years when the answers are still coming in, and that is a rare and quietly remarkable place to stand. Let that settle over you as the night goes quiet. Somewhere out there, right now, the rain is falling into the seas of Titan, and a sealed tube waits on the floor of an empty Martian crater, and an object we could not name is still gaining speed in the dark. None of it needs anything from you tonight. You can simply rest inside the size of the question and let the looking continue without you until morning. Sleep well and good night.